Hello, this is Concrete Path and third lecture of that ILDs is going to be started. Let's go. Let's go for that one. So we have the topic what we call as maximum shear force, maximum bending moment. Now for this topic, we have different loads. Loads can be of different nature. So first load combination is that if you have, we need to get the maximum shear force and maximum bending moment due to moving loads. Now first kind of load is that if we have single point load, it can be occupied anywhere on the beam. Single point load. Second one is that when you have UDL of length d greater than the span length, span of the beam, span L of the beam. And third one is that UDL of length d that is lesser than the span of the beam. Then after that we have fourth condition, that a series of loads, we call them as series of concentrated loads or series of wheel loads. A train of wheel loads, we call them a series of concentrated loads or train of wheel loads. Multiple number of loads are moving on the beam. Let's take the first case, that's talking about that only one load is moving along the beam, single point load. For that we need to get the maximum shear force and maximum bending moment because of that moving load. So let's take the first case. So case 1 is that single point load. Because of single point load, we need to calculate maximum bending moment, maximum shear force at any particular section. Let's say at section C. You have some section C's, you have taken that section C. I want to say because of that particular load is moving, we want to say what is the shear force maximum and what's the bending moment maximum we can have along the beam. But at a particular section C, let's take that, I would say you have the simply support beam. Let's take any section C. I know that if this is at a distance of x from the support A, and this is L minus x, this part is L minus x. I would say the SFD diagram looks like, I know that how the SFD looks like for the simpler case. That looks like in this fashion, minus plus, and this one is your x by L, this is your L minus x by L. Now the possibilities are that if I write what should be the maximum positive maximum shear force at point C, at the section C, I would say you place the load at the maximum ordinate, positive ordinate, that's your L minus x by L, and I would say that load P kilonewton into that ordinate, and this would be your maximum shear force at C. And now if you want to calculate negative maximum shear force at C, that would be equals to, if you place that load on the maximum ordinate of negative part of that ILD, I would say that part of the ILD is negative minus x by L. You apply that load on that ordinate itself. That means P times P kilonewton into that ordinate of minus x by L. So it would be a negative shear force. And you got these two values. Now, if you talk about one more thing is that we call as absolute maximum values. We call them as absolute, you can write absolute maximum values. Absolute maximum values of shear force and bending moment. If you talk about V absolute maximum, and that also positive, what should be that value? You got the value of that at particular section C, what is the maximum ordinate at that particular location. Now if I want that anywhere in the beam, that's what absolute means, that you can have anywhere in the beam. Wherever you can find maximum, that's your absolute maximum value of shear force and bending moment. Now the V positive maximum was at particular section C. So now if I analyze this SFD diagram, can you tell me what is the reaction at A, ILD for reaction at A? Is this in this way? And what is the ILD for reaction at B? is that also positive? This is also positive. Let's say both are positive, but I reversed the direction of reaction B. This is 1 unit, this is also 1 unit. This is reaction A, this is reaction B. Now, but the thing is that if I combine them, let me try to combine them. Here we can have. Now, this is our profile of that reaction A, reaction B. Now, if I say, what is the shear force diagram at any particular section C? What is the shear force diagram at any particular section C? I would say you go some downwards minus A by L. Then after that you go from the other side some B by L, such that your shear force diagram at particular section C, there is some support C. I would say this is your A by L and this is your B by L. Can you tell me what is the slope here? Can you tell me what is the slope here we can have? We know that's ordinate of 1 for the length of L. Similarly here the slope is ordinate L, that ordinate of 1 for the length of L. And if I tell what is the ordinate here for the upper triangle, I would say that ordinate is this ordinate for the length of B, it is B by L, because theta is 1 by L. And similarly from the bottom, I would say for the bottom triangle, I would say you have this ordinate of 1 for the length of L. And if I want to calculate for the length of A, I would say this is A by L. So this was your that moment, that what we call as shear force at C. So you got some negative shear force at C, and similarly you got some ordinate of B by L in the positive side. Now if I want to say what's the maximum absolute value of shear force we can have, let's talk about V absolute negative. What is the negative absolute bending moment absolute shear force we can have? I would say if the value of X is such that your section is at the support B, if the value of X is such that it's at the section B, then I can draw the SFD like in this fashion. Let me have that. Let me show that. Let me try to show that now. I would say the diagram would be in this fashion. Let's say in this fashion, such that if the X is very small, if this is L minus X, it tends to 0, because we are saying that value of X is at the support itself. If I try to make that diagram, that would be in this fashion. Can you see that small triangle? So the diagram would be in this fashion, that shear force diagram, similar to that of a reaction at B, similar to that of reaction B, but we are talking about shear force, that's negative. So if I try to make that diagram in this way, such that it's that smaller triangle tends to become 0. It tends to become 0, such that your absolute maximum shear force can be developed. Do you got it? Similarly, if you try to make positive shear force diagram, but you want to calculate maximum absolute value, I would say if the value of X is such that it is almost equals to 0, if it is almost equals to 0, then I know that shear force diagram variation, how that looks like. I would say that would be in some sort of fashion. Bottom is that X by L, and from the top it is L minus X by L. Then after that a linear variation 1 by L. If the value of X is 0, that means this part is 0. So finally we say that at the support itself, at the support A, we have some ordinate of 1, and this is your positive V max we can have. And from this one we can get absolute value of positive shear force. Now if you want to calculate what is the absolute shear force at positive shear force absolute, I would say you place the load on the support A itself, and you place the load here, and ordinate is 1, so final load of P kilonewton into 1, that's P kilonewton. And similarly V absolute negative, maximum mean is it's talking about absolute. So V absolute negative, I would say you have this triangle of shear force diagram, and such that its ordinate is maximum at the support B, and you place the load here, and you would get a maximum ordinate of minus P kilonewton. Finally you get a negative absolute shear force of minus P kilonewton. Do you got it? Now second one is that what we call as absolute that bending moment at C. Let's take the bending moment at C now. Do you know that variation of bending moment? That's AB by L at particular section. So this is your X, B by L, AB by L. Now This is your ordinate. Now you want to say, because of the single point load, where should be that load placed such that we can have maximum bending moment at C. So if I place that load at the maximum ordinate of YC, this is your YC ordinate at C. If I place the load at this location, I would say your maximum positive bending moment at C is equals to this is maximum, and this is equals to some P kilonewton into some ordinate of YC, some meters. So you can get the value. Now if you talk about what's the maximum bending moment we can have, that we can call as absolute bending moment, See, I know the variation of that bending moment is in this fashion. Now if I take that section should be at the midspan. If I take that x equals to L by 2, at that point if I calculate, I would say maximum ordinate is possible here only. At all other points of x, you would have some variation in this fashion, such that your maximum ordinate is not such that some ordinate is there, but it's not greater than this value. This is, let's say this is some 10 value, this is 9.8, this is 9.3, 9.6, some values we have of the ILD. Similarly, from the other side also, you can have some values, but you won't be having that maximum ordinate anywhere other except that when x equals to L by 2. So for that, if you substitute what should be the value of YC, I would say that equals to L by 2 divided by L, AB by L. So that's the ordinate of L by 4, ordinate of L by 4. So accordingly, I would say what is the maximum absolute moment because of that point load, single point load. I would say P kilonewton into ordinate of L by 4. So P L by 4. You already know that if that point load is acting at the midspan, we have maximum moment of PL by 4, bending moment PL by 4. Second case is that, now let's take the second case that we have when UDL length of D is greater than the span length of the beam L. So let's take the second case. That's what we say. Your second case is that UDL of length D greater than the span length L. There is a span split support beam having span of L, and we say this is greater than D. Now to take that, to take a shear force and bending moment at any section C, we are talking about section C. Let's have the section C somewhere. Let's say there's some section C. I would say this is your shear force diagram. ILD for, this is not shear force diagram, this is ILD for shear force at C. So this is negative, positive. So I would write this is x by L, this is L minus x by L. Now for the positive shear force, for the positive maximum shear force at C, I would place the load only on the positive side of that, because since even the load is UDL and it's having length more than the total length of the beam, but still I won't be applying the loads on the right side. I won't be applying that. I would be applying only for this part only. I would be only applying the loads on this part only, on the positive side only, such that I can have positive maximum shear force. So I would say you have some ordinate of L minus x by L, and you have some length of L minus x. So I would say your V positive maximum would be equals to area of that area under the UDL. That's area under the UDL. In the positive side into that intensity of UDL intensity. So if I calculate that, I would say you have some intensity of W kilonewton per meter, and area under the curve is equals to 1 by 2 L minus x by L into length of L minus x. So you got a value of W L minus x whole square by 2L. This is your shear force. Maximum we can have positive shear force at C. Now if you talk about maximum negative shear force at C, that means you have to take the, if I write that negative maximum shear force at C, I would take this rectangle as then apply the loading only on this part only. Negative, that is your UDL of W. In here the ordinate is x by L and length is also x. So I would say 1 by 2 x into x by L into intensity of W. So W x square by 2L. That's negative. Now let's say that I apply load in this part also. That means this part would contribute some positive that shear force. This part might contribute some shear force positive. If I add that, that means your that negative shear force gets decreased. So if this was your some minus 20 kilonewton, if this contributed some 10 kilonewton positive, so net value of minus 10, and that is lesser if we compare in terms of absolute, that 20 is greater than 10. That means this has got decreases. So negative shear force got decreased. So we have to ensure that we only keep on one of the sides that load, such that your load, such that overall effect is maximum. Now third, for this case also, we can talk about that absolute V absolute. If I talk about V absolute positive, that means the value of x should be such that you have only, that means x should be 0. That means if you talk about that section itself, that reaction at A, in this one I can show where it has gone, the beam. So beam is somewhere here. If I say, if I keep that, if I keep the value of x such that, if I keep the value of x such that a section is at the support itself, I would say the diagram of the SFD would be in this fashion, that ILD for SFD. Then accordingly I can have some positive diagram, positive. So overall intense ordinate of 1 would be here, because this one is ordinate of 0, because x by L, that is 0 because x is 0. Then I can say for the absolute, what's the V max absolute we can have? I would say ordinate of 1 for the length of L, intensity of W. So 1 into W into 1 by 2, L into 1, so WL by 2. So that's what we have when you have a simply support beam subjected to entire load, that maximum UDL, that UDL for the entire span. We know that shear force would be equals to, that reaction at B would equals to WL by 2. When I draw the shear force diagram, that is in this fashion, WL by 2 maximum ordinate, we can have WL by 2. And similarly, you can have negative, similarly from this side also you can see negative WL by 2 for this part. If the value of x is such that x equals to L, I can get V absolute negative. This is 0. So I can get ordinate 1 L, I would write 1 by 2 WL into 1 negative, that's also WL by 2. Now if I talk about bending moment, if I talk about bending moment at section C, so I would say this is some x value into L minus x divided by L, AB by L, and I place the, because entire BMD ILD is positive, entire ILD for BMD for bending moment at C is positive. So I would place the UDL for the entire length. I would place the UDL for the entire length, because all is having positive, so I can get a positive M positive maximum at the section C. That would be equals to area under the UDL. Area under the UDL equals to 1 by 2 length of L, ordinate of x into L minus x by L, and intensity of W. So you got some value there is equals to W into x into L minus x divided by 2. And if I substitute, what should the maximum absolute value we can have for the bending moment? If I calculate M absolute, that maximum we can have for this case anywhere on the beam, I would say at the midspan we can have maximum ordinate. Do you know what's the maximum ordinate for a beam subjected to UDL for the entire length? WL square by 8. I want to see whether this value would give me same value. Whether this equation, if I substitute value of x equals to L by 2, that means the value of the section C is at a distance of x equals to L by 2 from the support A. I would say W into L by 2, L minus L by 2 divided by 2, that's WL square by 8. So this is your absolute bending moment for this case when UDL is having, when the UDL is such that UDL length D greater than the span length L. No, we got the two cases. Can we take yeah, we got the two cases. Now we can take third case of. These two cases are easy. Now we can take the third case. Now the main problem goes from the third case and the fourth case. So let's go for the third case. That's UDL of length L. Yeah, UDL of length D. That's lesser than the span length L. Span length of the beam L. Now we have some beam of length L, and there we have some section C. Add some x from A. Then we have some UDL of intensity W, and its length is only D, such that D is lesser than length of L. So for this case, we want to say what is the shear force and bending moment at that section. Let's have that shear force diagram. I would say the shear force diagram would be in this fashion. ILD for shear force diagram, not shear force diagram, it's ILD for shear force diagram at C. So I have this value of x by L, they have this value of L minus x by L, this is negative positive. Now for the, can I say for the positive, I would say for the positive absolute, not absolute, positive shear force at C, positive shear force at C. Positive shear force at C. For that, I have to place that load UDL such that for this length of L minus X, it might be having, so it depends on the length of that L minus X, how much length of this one is there. For general case, let's say value of X was 3 meter and L minus X was equals to, let's say 7 meter and your D was equals to 5 meter. Then for the value of positive, for the positive diagram, I would say keep all that 5 meter on the positive side such that I can have positive shear force diagram. Then accordingly, I would have some ordinate here. I would say the value of V positive maximum would be area under that 1 by 2. I can say area. There might be some area under that curve, under the UDL, area into some intensity of W. So this is your positive one. And what there is one more chance that if the let's say that this was your 7 meter, UDL was 7 meter. Second case that when the UDL was 7 meter and if the L minus X is only 5 meter, so that means other part of the UDL is outside that what you call as outside the point B. You don't have to keep it on the negative side because it would contribute a negative shear force, so that would give you lesser value finally. So you try to keep it on the positive side only. So rest of that part, it's outside the beam, you can ignore that part, it would contribute 0. If you keep that in the right negative side, it would contribute negative, so you don't have to keep that negative. Best is to keep that value of 0 rather than keeping it negative. So I would say if the length of L minus X is 5 meter and value of D is 7 meter, I would keep for the entire length. I would write total area total into intensity of W. Okay, now this was your positive. That means the condition for the V positive is that we call that if the load was acting going from left to the right, if this is left, this is right, this was the condition that if the load is going from left to right, that means we call this as tail, we call this part as head for that case. That means for this V positive maximum, this can be an objective type question, that for the V positive maximum, for the V positive at C to be maximum, the head, I would say, the tail of the UDL should be reaching that section. UDL of that tail of that what you call as UDL should reach that section. If you have this ILD for shear force, this is positive, this is negative, and I want that V positive to be maximum. So I need to keep that UDL just after this section. I need to keep it on this part. I need to try that it's on the maximum ordinate. But if the length is very much, I would keep other part outside the plane, such that your tail should be at this point. Critical thing is that tail should be, you write that tail should be at section itself. Let's say just after section, such that to avoid the confusion that it should be on this side. So it should be on the other positive side only, on this positive side. And for the negative, if I talk about negative, there are different possibilities. So for the negative, if you see this value is X equals to 3 meter and intensity is very much, and you try to, in this case, you would try to keep that for the V negative. If I write V negative, for the V negative, for the shear force at C to be negative maximum, I would try to keep that load on this side, such that no load is outside this one. So that there is no load on this side, I would try to, that means head, I should keep that on the section. So I have to keep that head on the section. So the rest of that part can be outside that beam also. So in this fashion you can have, or if the length is lesser, so you can have only this smaller part. But you have to ensure that head is on the section, head on section. You don't have to go out of that. Out of that. Okay. Now for the absolute one, you already know that if you want V positive absolute, you can do one thing. You have that V positive absolute. We know that the diagram looks like this one. V absolute maximum. That means that is also equals to shear reaction at A. So for that, you place the load. You try to place the load. That means if the load was moving from left to right, you try to keep the tail on the P coordinate. You try to keep the tail on the P coordinate. Then after that, if the length of D is up to this point only, so you can have more area. If the length is more, so you have more area here also. But you have to ensure that first you fill this part. First you fill this part, then after that you can have other part of the beam, other part of the loading also if there is. Now for the what you call as absolute positive bending moment, now we are talking about bending moment. Let's go for the bending moment. And this is our main problem of that third case. This is our main problem of the third case. Let's go for this one. Now this is your section C. Add some x from A, and this one is L minus x. This is your important one. Let's write this as important one. Important one is this one. So there's some UDL, and let's say there's some UDL of D, length D, and but that length is lesser than length L total, length of beam. So I would say you partly place, let's say you partly place it on both sides, of section C. You partly try to place it on the both sides, such that we already know that. See, we already know that you have the ordinate here maximum, and near to that region, on the neighboring sections, we can say on these points, if the load is UDL is somewhere here, we can have maximum ordinates here. Some ordinates we can have. So more area would be here. More area is more here. So if the load is also here, if the loading is also here, UDL of length D, so we can have more area closer to that section. So I would say you partly place some of the UDL on one side and partly from other side. Now we want to see how much we have to place on one side and how much on the other side. So we need to get some equation or condition for that. So we have to derive that condition now for this one. Okay. So for that, let's say that let's make the mahol banate hain. Chalo, I would say, let's say a part of the UDL is on this side and part of the UDL is on this side. Let's say the total, we already know total is D. I would say on the left of the C, I would place part of the UDL that's having a distance of, that's having a length of Z, and from this side we have length of D minus Z. Okay, this is Z and this is D minus Z. Now I need to calculate for this one. What is the moment at C developed? What is the moment developed at C? I know the equation that, what is the ordinate at C? This is the ordinate at C, YC. Ordinate at C, YC. Can you calculate YC? That is X B by L, AB by L, AB by L. Do you know that? This is ordinate at C. And let's say the ordinate here is Y1. Let's say the ordinate on this point, this is what ordinate of Y1, and ordinate on this side, this is ordinate of Y2. Now, can you calculate the moment? Can you calculate what is the moment? Can you calculate what is the moment at the point C? And we want it to be maximum. So let's try that moment at C from the ILD. I would say area under the UDL, area under the UDL into intensity of that UDL. Let's say the intensity is W. So I would write moment at C to be maximum is equals to area under the curve. I would say 1 by 2 semi-parallel sides, 1 by Y1 plus YC. For what is this length? Can you tell me what is this length? For the length of Z. And plus area of the next trapezium, that's YC plus Y2 for the length of, what is this length? This is D minus Z. So D minus Z. And whole we have multiple of that intensity of W. I want this value of MC to be maximum. to be maximum. I want to maximize it. So what can I do? I would say let's go DMC with that of a DZ, because your value of X is fixed. I would say X is fixed because section C is fixed. Section C is fixed. Now we want to see at this particular section, at particular X of a particular location of X, that is a particular location of C from A. I want to say what should be this value of Z? What should be this value of Z? That's variable. I want to see how much amount of that UDL I should place on the left of that section, and on how much of that T minus Z I should place on the right of that section. So your variable of Z is there, not value of X. So value of Z is that variable. So I had to differentiate that moment with respect to that Z. So DMC by DZ. I had to go DMC by DZ. I have to equate it with that equals to 0. So from this equation I can have that, which implies that 1 by 2, then we have y1 when you differentiate it with respect to Z, so you are left with y1 plus yc, and from the other part we are left with 1 by 2 yc plus y2. Now if you differentiate with respect to Z, with respect to D, that is 0, and if you differentiate it with respect to Z, that is -1. So you are left with -1, and W, we can ignore that. W goes to 0, so we can say this part is equals to 0. This part equals to 0, so you can have y1 plus yc equals to y2 plus yc. So that means y1 equals to y2. So that means ordinate on the value of Z is such that the ordinate at on this side, ordinate at tail and ordinate at head is equals to same. So the conclusion is that, so let's write the conclusion, and this is a critical thing that we have. Let's write the conclusion that for moment at C to be maximum, that means the loading should be such that, yeah, value of Z should be such that ordinate of ILD for bending moment, ordinate of ILD is same at tail and head of that UDL. That means ordinate of ILD is same at head and tail of the UDL. Y1 equals to Y2. And for this condition, we want to see from this triangle, we want to see what should be the condition we can have. We can derive one more condition here. So if I say what's the value of Y1 and Y2 from these triangles, we need to get the values of Y1 and Y2. Let's try to get those values of Y1 and Y2. So I would say your value of Y1 is for the length of, what is this value? Can you tell me what is this value from the support A? The total length was up to this point X. Support C was, section C was at X from A. And if this is Z, that means this part is X minus Z. So by the similar triangles, I would say value of Y1 equals to, I have the equation that Y1 equals to Y2. I want to play with this equation, Y1 equals to Y2. So if I write Y1 equals to that Y1, what should the value of Y1? Can you tell me now? By the similar triangles, I would say it is equals to YC, but YC was for the length of X, but I need only for the length of X minus Z from the similar triangles. Similarly, from the other side, we can say what should the value of Y2? Can you tell me what is this value equals to? What is this value equals to? Total length was L minus X, and you subtract that D minus Z. I would say YC for the length of L minus X, but I need for the length of L minus X, and minus, let's write that L minus X minus one more term is that D minus Z. So I have this equation. Now we can say this goes, and we can simplify it. We can simplify this equation now. Let's try to simplify it. I would write that X minus Z L minus X is equals to X times L minus X square, and then this one is negative, so finally it becomes negative XD, and we have minus becomes plus Z into X, so plus X into Z. So this value we have we have this value, negative, negative, positive, positive. And we want to see from this side, this is XL, then we have minus X square, we have minus ZL, we have minus plus ZX, that equals to XL minus X square plus. So we have this equation. Now we can say XL goes with XL, and double X goes with double X, and ZX goes with ZX. So we are left with minus ZL equals to minus XT. Now, if I try to not rotate, if I try to have it in terms of X by L is equals to Z by D. Now, just think of this one and see what this is. X by L, Z by D from this figure. X by L, Z by D. So from this one, let's try to write a statement now. So I would say, what is this value of X? Can you tell me the value of X? So value of X, if we write that, what do you mean by these values? Let's write here from the side. The value of X is equals to the location of section from A. The location of section from A. X is the location of, that is AC. X equals to AC. That's why the section is from the A. And length is total length of AB. That is the total span length. And D is the length of what you call as, D is the length for that what you have UDL. D is the length of UDL. After that, Z is the length which we have to keep on the right side. So Z is on AC side, I can say. And similarly, I can write D minus Z will be on, D minus Z is on CB side, BC side. And similarly, L minus X is on BC side. So I would say for your AC side, you have some length of X. On that side, you have to keep Z amount of UDL. With respect to the total length of L, you have that side of AC equals to X, and on that, and from the UDL of D, total D length, you have to keep only D amount of that length on the AC side. So if I try to make that, so this was derived from the condition that M was maximum, moment at C was maximum. So if I write that condition that for let's try that by this color. I would write for, let's try to zoom in out, zoom in. I would say for moment to be maximum, for M at C to be maximum. So you got this equation that X by L equals to Z by D. This was your section, this was your Z, this was your total D. I would say this was your length of X. Let's try to have it where, yeah, in this fashion. Say this was your length of X. Let me try to have it one more time. So for the length of X, you have to keep the UDL only by this amount, small d, that small z, small z, small z. So we can make the statement that for moment at C to be maximum, you have that section C should be such that it should be such that we know that is fixed, but it should be such that based on this one, it should be such that it divides the beam, it divides the beam in the same ratio, of expel, as the ratio of, as in the ratio, as it divides what you call as it divides the load, as it divides the UDL in the ratio of ZBL, because your XBL is same as that of ZBL. It's when we, it was derived when we said moment at C, at this section C should be maximum. So we have this statement that for moment at C to be maximum, section C should be such that it divides the beam in the same ratio of X by L as it divides the UDL of in the ratio of Z by L, because X by L is equals to Z by L, so ratio is same. So that's your statement from this one. So we got the absolute, we got the moment at C to be maximum. Now second thing is that we got at particular section C. Now we can say for the absolute bending moment to be there, where should we have that moment C to be maximum? What should be that section C such that your moment is absolute? I would say the condition for that, obvious condition for that, is that if you have that ordinate of YC to be maximum at that location, I want that section where ordinate is maximum at that location, there is a chance that maximum absolute moment is there. There's a possibility that absolute maximum bending moment is possible at that location where your value of ordinate C, YC is maximum. So I need to maximize that ordinate of YC, and from that I can get the that bending moment, absolute bending moment value. Let's try to maximize that value of YC, because at that value of YC, at that particular section of C, your YC is maximum, and based on that I can have maximum area under that UDL. So let's try that for the statement. Let's try the statement. I would say I would write absolute maximum bending moment, absolute maximum bending moment anywhere, we can say anywhere. So for that condition, it's obvious, you can write obvious is that your YC is to be maximum, has to be maximum. That means you take any section such that on this particular YC you have maximum ordinate, and if accordingly if you have that area under that if you have that area under that UDL, so there is a chance that this area is maximum. So based on this one, you can have, which implies your area would be maximum, area under the curve would be maximum, area under the UDL, so that would be maximum. So I have to maximize that YC. So YC, so now that means YC is a variable, I have to maximize it, but with respect to what I should maximize it? Is it with respect to Z or is it with respect to X? So why, I don't know. If I know directly that C is at 5 meters from A, then I can directly calculate YC is equals to AB by L. I can directly calculate, but I don't know the value of YC, where the location of YC is. So I need to check the value of X, where the value of YC would be maximum. So I want to think of it with respect to value of X, value of section. So let's take that particular value of X. I would say I have to differentiate it or maximize it with respect to that location of X. That means X is the location of that section C. So dyc by dx, that equals to 0. And to calculate that, what's the ordinate here for a beam? We know that that's a simply support beam, that's AB by L. AB by L. So I would write X into L minus X by L. So that I have to differentiate that d by dx of this function equals to 0. Now, if I solve it, I can get that xl minus 2x equals to 0. X equals to, is it correct? Yeah. XL minus, yeah, I would get a value of L minus 2x equals to 0. So after differentiating, I got this value, and finally I would say X equals to L by 2. That means it's saying that you take that section where the X equals to L by 2. That means at that location you can have maximum ordinate. You can have maximum ordinate of what you call as, what do you call that as? That X equals to L by 2. So maximum ordinate is L by 2 divided by 2. Yeah, AB by L, that's equals to L by 4. maximum ordinate of L by 4. Maximum ordinate of L by 4 is that then you have some UDL and you have that area under that UDL, so you can get maximum absolute bending moment maximum. Now you got the value of x equals to L by 2. Now if you substitute it with respect to that section C, we have that derivation. We got this equation of, if I use this equation now, that x by L equals to z by d. I want to see one more thing here. X by L equals to z by d. X by L equals to z by d. So on this location, I got that section should be selected at midspan. I got this from this condition that the value of x should be equals to L by 2. That means section C should be at the midspan of the beam. I got from this one. Now we have one more thing, that x by L equals to z by d. We have this length of d, and z is from this section C to some length of z here. So I would, if I use that, if I substitute the value of x equals to L by 2, that equals to z by d. So what we get from this one? Do we got z equals to d by 2 also? Do you also got z equals to d by 2? So for this case, if you try to draw that ILD for BMD at C, at the location where it's saying that YC is maximum, so YC is equals to YC max. For this condition, YC is YC max, and it's saying that from this conclusion now, it's saying that for the M at C, now we have selected that C because from this one we got that x of C, location of C is at L by 2. Now for if I write that statement again, if I show that statement for bending moment at section L by 2, that at midspan to be maximum, so section at midspan should be such that it divides the beam in the same ratio of 1 by 2. That's because x is L by 2, so 1 by 2, as it divides the UDL also in 1 by 2. So that means UDL should be equally spaced from the both side from the section C. So part of that, so equally should be placed from the both the sides. Yeah, it should be placed from the equally from the both sides. So if you have some UDL, if you have some UDL of d, I would say z equals to L by 2, yeah, d by 2, and this is also d by 2. Then we have some ordinate here, such that ordinate 1, we already know that ordinate 1 was equals to ordinate 2. This is also ordinate 1. We already know that also ordinate 1 is equals to ordinate 2. And from this one, you have this area under this UDL. You have some UDL, and area under this UDL, you can say this is your absolute magnetic moment, M absolute. You can calculate that also. And one more conclusion, once you draw that, I would say that there would be some resultant of that loading. Can you tell me what the resultant of that loading would be? There would be some resultant of that loading. Where that would be? I think that would be somewhere here at the midspan itself. So we can write one more statement that we can write that one more statement. Let's try to write that. Where we have that one more pen. So this one. So let's try to write that. Where we got that pen? This one. Let me try to write a statement here. I would say, so for the absolute bending moment, at the rate of midspan, what the statement is saying, that means at that location, CG of the loads will be at the midspan. CG of the loads would be at the midspan. So when you calculated that, what should be the maximum absolute bending moment? So for that we say, first you check the YC, where should be the YC to be maximum? At that location we say YC should be, that section should be at L by 2. And from that condition I said, what should be the value of maximum absolute moment? I said that your Z equals to D by 2. That means loading should be equally spaced from the center. That means your centroid, your CG of that load, entire load, there would be some resultant that is passing through the centroid, center of the beam. That's what it's saying. For the absolute bending moment at the midspan, your CG of the loads is passing through the midspan. Okay, this is one more conclusion from this one. So we had three, I think we had three conclusions from this derivation of that when UDL was lesser, UDL length D lesser than the span length L. Now the fourth case, I think we should take a problem. Then after that, we can take the fourth case, that is the train of wheel loads. We can take, then after that, the train of wheel loads. So let's write this. Let's write the problem now. Let's take the problem. Then after that, we can have the case 4. Let's write the problem that we have. Problem 27. Simply support beam, 15 meter length. Simply support beam, 15 meter length. Okay. Simply support beam, 15 meter length. 15 meter length. Section C is at 6 meter. That means X equals to 6 meter. That means this part is 9 meter. And here we have simply support beam. Now, what is happening there? The UDL is there, but UDL length is small d, that is lesser than the span length. So UDL of 40 kilonewton per meter for the length of 5 meter only. That means D is equals to 5 meter. D equals to 5 meter. Now it crosses the girder. This is your girder beam. That means it can be used on the bridge. It's acting as a major beam. So so your beam of 15 meter is actually a girder. It's a girder beam. Main bigger beam. It's of depth, some sort of 1 meter depth. A girder beam. It crosses that UDL crosses left to right. It moves in this direction. It moves in this direction. Left to right. So we need to say what is the that negative and maximum, what is the negative and positive maximum shear force we can have at section C, and what is the maximum bending moment we can have at C. We know that section C is at 6 meters from A. So we need to say V positive, C, V negative, C, M at C. We need to get these three values. Let's have one by one. Can you draw the SFD? ILD for SFD? Not SFD, I forget that. ILD for shear force at C. There is a difference between SFD and ILD for shear force at C. So let's write that ILD for shear force at C. We have that variation. We already know A by L, B by L. This is a straight line. This is not a curved. So I would write A by L, B by L. So this is minus. This is A by L. What is the value of A? 6. 6 by 15. I can write 6 by 15. And this one is 9 by 15. This is negative. This is positive. And this is a vertical line. This is not a incline. This is a vertical line. You can have that. So this is your ILD for SFD. ILD for shear force at C. ILD for shear at C. Now, I would say, what's the V positive we can have? I would try to have this one. I would try to keep this one. And the loading is, I know this length is 9 meter. We have ordinate of 9 by 15 here. That is 0.6. We have positive diagram. And for the V positive at C to be maximum, I would try to keep the load. I would try to keep the tail of the load on the section itself. The tail, you remember that tail. For the positive, we keep that tail on the section itself. Then after that, we try to keep the loading on the right of that section. So what is the length of the UDL total length? Total length of UDL is 5 meters. So for the length of 5 meter, you have to use that UDL. That means there would be some ordinate here, and this is 5 meter. This is 5 meter. Can you calculate that ordinate? If this is 0.6 for the length of 9, can I get the ordinate here? Can you get the ordinate here? I would say that value of ordinate would be, can you get that ordinate? That would be 0.6 for the length of 9. I need for the length of 4 meter for this triangle, 4 meter triangle. So I got that ordinate also. I would say V positive maximum would be area under the curve. Area under the curve, that's sum of parallel sides. 0.6 plus 0.6 into 4 by 9. Into 4 by 9. You got this sum of parallel sides into length of 5 meter. Because UDL is for this one, 5 meter length. And intensity, what is the intensity we have of the UDL? 40 kilonewton per meter, 40 kilonewton per meter. And you can get the value of V positive maximum. That is 86.67 kilonewton. Then the second one is that V negative at C to be maximum. V negative at C to be maximum. So I can write V negative at C to be maximum. I have this diagram with a maximum ordinate of 6 by 15, that is 2 by 3, 2 by 5, that is 0.4, 0.4 ordinate, 0.4. Then what is this total length for this section? We have this 6 meter, and what is the length we can have for the UDL? 5 meter. So I can place the entire length. That I had to ensure that head of the UDL is at the section itself, because it's moving in this direction, so I have to keep the head. This is head. You can write head for the negative head, and for the positive you can have that tail. You can write that tail also there in order to remember that. So head here, so intensity of 40, length of 5. So can you tell me what is this ordinate? I would say this is ordinate of 0.4. It was for the length of 6 meter, but I need only for the length of 1 meter, because this one is 1 meter from this point to the loading. So I would say loading of 40 is there, kilonewton per meter, loading of 40, and length is 5 meter. And what is the area under the curve? So V negative at C to be maximum, we can write that is equals to 1 by 2 parallel sides, and length of 5 meter, intensity of 40 kilonewton per meter. You can have a V negative value of negative times, I can write 46.67 kilonewton shear force. Now I would say, what's the bending moment at that section C? Bending moment at section C. Let's have that section. Let's have the let ILD for bending moment at C. Can you draw that? Also? I would say this is your ILD for bending moment at C. What is the ordinate we can have here? That's YC. Can you get the YC here? Value of YC would be equals to AB by L. AB by L, 54 by 15. What is this value equals to? Is it 3.6? 54 by 15. 3.6 meter. 3.6 meter. So 3.6 meter is there. Now we have the concept of that UDL. Length lesser than the span length. So what was the condition for this one? For the moment at C to be maximum, what was the condition? We say that Z by D equals to X by L. That the sections should be such that it divides the loading in the same ratio as it divides the section, as it divides the beam. X by L equals to Z by D. If I substitute that value, if I use that condition, I can get the value of Z. Because I don't know the value, how much amount of Z I can take. I don't know what's the amount of Z I have to keep from this side. But if I see from the logical perspective, I would say, because your area from this side we have bigger triangle here, so more loading should be kept on this side and lesser loading should be kept on this side. If I have this perspective, I can say that also. But I had to use this equation. Let's try to use this. Z by D equals to X by L, and let's substitute those values. So I would write, what is the value of Z? I don't know. But value of what is the value of D? I know. Value of D is equals to 5 meter. What is the value of X? X is the length of section from the support A. That is 6 meter. So X equals to 6 meter. And total length is 15 meter. 6 by 15. So I can get a value of Z equals to 30 by 15. That's 2 meter. That means out of the 5 meter of the UDL, you have to keep 2 meter from the left of the section C and 3 meter from the right of the section C. Okay. So I would say this is your 2 meter and this is 3 meter. So Z is 2 meter, that D minus Z is 3 meter. Now there would be some ordinate. I already know that Y ordinate, Y1 is equals to Y2. This is some ordinate of Y, and this is also ordinate of Y. We have derived this one, Y1 equals to Y2. So there is some ordinate of Y1 and Y2. and the ordinates are same. You can get those ordinates of, since we know that from the similar triangles, yc is 3.6. So we can say, what is the ordinate at y? I would say 3.6 meter was for the length of 6 meter. It was for the length of 6 meter, but I need only for this triangle. What is the length of this triangle? That is 6 minus 4, 4 meter. So I got that ordinate of 2.4 meter. So I can now calculate the bending moment at C. So this is the area under the curve. This is the area under the curve. I would write M at C to be maximum. That is equals to area under the UDL 1 by 2 semi-parallel sides. That is y1, that is ordinate of y plus ordinate of yc, and it's acting for the length. Actually we can say it's acting for the length of 2 meter. See what we can do directly. It's acting for the length of 2 meter plus then we have next triangle, next trapezium, we have ordinate of 3.6, and next ordinate is 2.4 for the length of 3 meter, and we have some loading of 40 kilonewton per meter intensity. Now once you know that the ordinate y1 and y2 is same, so we can finally we can also write it in this way: 1 by 2 2.4 plus 3.6 ordinate of meter, and for the length of total 5 meters into 40 kilonewton per meter. Because this part is same, so we can write 2 plus 3 equals to 5. So we can directly write that also. So you got that, and that comes out to be finally 600 kilonewton meter. So you got this one also. Now then the fourth case of that moving loads is that train of concentrated loads, or train of wheel loads, or series of concentrated loads. Let's say that we have train of wheel loads, that we have concentrated loads, train of wheel loads. So for this case we have 5 conditions. We can have 5 conditions. In this case D, we have 5 conditions to be checked for this case. So for the let's write that case D, that's train of wheel loads. So there might be load 1, let's write load 5, load 4, load 3, load 2, load 1. They are acting there would be some center to center spacing between the loads, and we say they are moving in left to right direction. They are moving in this direction. Now there would be some beam. We would be having some beam. Now there we have to calculate that shear force positive at C, shear force negative at C, V absolute at C, V negative absolute at C. This is absolute. This is maximum at C. Now this one is your absolute. This one is your absolute. It's not about at C. It's at anywhere. This is anywhere. Because absolute is anywhere. You can calculate that M absolute also anywhere. So these are your one case, second case, third case, and one is your moment at C to be maximum. This is your fourth case. Now fifth case is that you have that moment at C, not moment at C, I would say moment under point load. Moment under any load point P2, or we can write Pi to be maximum. I want that under that particular load, I want that M to be maximum under particular load P2. Let's say that is P2. I want that also. So 5 conditions we have from this one. Other 4 we have already dealt with how to go with them. And for the fifth case, we have one more, that's under point load. Under particular load, I want to say under this load, what should be the maximum effect we can have? Okay. Now, if you talk about that shear force diagram bending moment, if you talk about ILD for shear force, we already know that you have some beam. The shear force, ILD for shear force would be in this way at section C. So we have some value of minus x by L, and this one is your L minus x by L, positive, negative. Now the thing is that we have different amounts of load. We have different loads, train of loads. Now I want to say For the negative shear force for the negative shear force to be maximum, what can you do? So there might be number of loads with some span, with some center to center distance. I want to say, let's say we have 5 loads, 1 2 3 4 5. Let's write it in this way. Let's say we have 5 loads, 1 2 3 4 5, 1 2 3 4 5, and we want to say where should we place the loads in order to get that V negative maximum. For the V negative maximum, there are different possibilities of that loads, of different loads. That means we have to ensure that one of the load is on this. If I have this negative, I would say one of the loads should be at this one of the load would be here, one of the load would be here, and one of the load would be here. So this is your case one, and it depends on the loads, that what is the peak load we have out of those, and it depends on the that center to center distance between them. Accordingly, we can say, so we have to perform different number of trials in order to get the maximum value of that shear force. So there might be one of the chance would be such that you place some loads on this side, negative side, and few loads you place on the positive side also, and still we can get V negative to be maximum. If you place some load, let's say you placed some load that was 2 kilonewton on the right side, but your 100 kilonewton you kept it on the positive side, so its effect was negligible, but 100 kilonewton was here at the peak coordinate of negative. So there are different trials we can write. Trials are there, we have to check for trials, but you have to ensure that one general thing is that for the negative side, for the negative shear force to be maximum, we say you keep most of the loads on negative side. You keep most of the loads on negative side. This is the general crux, negative side. And similarly for the V positive maximum, you keep most of the loads on positive side. Most of the loads on positive side. Such that then there might be different trials, 2-3 trials you have to perform. The problem is such that you generally have to perform 2 trials. 2 trials are enough, I think. Most of the problems are designed in a way that you perform 2 trials and you can get the Vmax accordingly. So this was your V negative, V positive, and third one is that V absolute. We already know that V absolute. For that case also, let's say V absolute positive, maximum positive absolute moment. So let's say ordinate here is 1, and we can have different loads somewhere here. We can have different loads, and we can check the different configuration. One few loads we can take outside also. So we have to ensure that we have to perform trials. We have to perform trials for this one also, shear force. So this we have to you write just we have to perform trials. Let's try 2 to 3 trials we have to perform in order to get which value would give maximum shear force. Now the third thing is that bending moment at C to be maximum. Bending moment at C to be maximum. Let's take any section C. At that point, if I draw the ILD, if I write that ILD for moment at C, I would say there is some variation in this way, and value here is YC. We know value of YC equals to X minus AB by L. We write AB by L, X into L minus X divided by L. Your YC ordinate of X into L minus X by L. So you had this positive diagram of ILD for moment at C. I want to maximize that moment at C. I want to maximize that moment at C. I would say one thing, that I try to keep the loads, some loads on one of the side and few loads on the other side. Similar to that of previous case when I said that Z by D equals to X by L. So few loads I keep on the one side and few loads on the other side. Similarly, if you have number of point loads, I would say let's keep few loads on this side and let's keep few loads on this side. Now the thing is that we make a mahol. Let's make the mahol. चलो mahol बनाते हैं इस question में. We say there might be some resultant of loads on the right side. Let's call them as resultant 1, or let's write by the badal pen से लिखते हैं. Let's write this one is your R1. There might be resultant of loads from the section on the left of section C, and there might be some resultant of R2 on the right side of section, and they are spaced at they are spaced at a distance of d. So the distance between those resultants of d r1 and r2 is distance d. Ordinate at c is yc, and let's say at this particular location of where the resultant is acting, there might be some ordinate of, let's say the ordinate here is yc, y1, and here the ordinate is, let's say the ordinate here is y2. So you got this one. We have some resultant here r1, we have some resultant here r2, and we have some section here, and we have some that what you call as ILD for that one. So at this location of r1 we have some ordinate of y1, and at this location we have some ordinate of y2, and the distance of r1 and r2 is equals to d. Okay, so this is your mahal of the question, and we say your section is at x from c, x from a. Your section c is from support a by a distance of, separated by a distance of x. So this is your x value. Now I would say let's keep this value as z, value of r from the c, value of r from the c. Let's say this value is z. So this is your mahal of the question, that this is your mahal of this derivation, that this value is z, this value is z. Similar to that of if you had UDL, we said from this section we keep on this side z, and from this side d minus z. Similarly from this side this would be up to the resultant d minus z. Okay, other things are also same, other things are also same. Now the thing is, r1 is the resultant of loads on the left of c, r2 on the right of c, d is the distance between r1 and r2, r1 at z from c. Okay, now the thing is that I want moment at c to be maximum. I want moment at c to be maximum. Now I would say effect of all these loads on the left of side, they are substituted by an equivalent load of r1 acting at a distance of z from the section c. If I try to calculate that, what is the moment at, if I try to calculate what is the moment at c, so if I say what is the moment at c, can you get the moment at c? I would say some r1 is acting and with some ordinate of y1 on the beam. There is some load of r1 acting here, and the ordinate here is y1, plus there is some load of r2, total load of r2. This is the resultant of loads on the right, r2 into some ordinate of y2. So I got the moment at c. I want to maximize this value. I want to maximize it to be maximum. So with respect to what should the variable we can have, with similar to that of previous problem when UDL was d length less than the span length. We differentiated there also dmc with respect to what you can call dz, because z is variable. We don't know where the centroid of the load should be, so z is unknown to us. But your x, that is section, is fixed, x is fixed, so z is variable. So we need to do dmc by dz. But we need to keep that y1 and y2 in terms of some yc, such that we can have some function of z. Let's have some function of z by the similar triangles. I would say, what's the value of y1? Can you get the value of y1? I would say value of y1 is yc times yc for the length of x, but I need for the length of smaller triangle, that's x minus z. For this triangle I need x minus z, and y2 is equals to, similarly from the other side, I would say yc was for the length of l minus x, but I need for the length of l minus x minus times d minus z. For this triangle also I need this triangle also for this one. Then I can solve this one. So I can write now is equals to r1, value of y1 is yc by x minus z, plus r2, then yc by l minus x, then we have l minus x, then we have minus, or we can write directly now, directly we can write l minus x minus d plus z. So you can remove this error bracket from there, bracket plate you can remove, you can get this one. Now we got this equation, now I want to differentiate it with respect to z. So I would say d by dz of this equation, d by dz of this equation. So let's try to solve it. We would see what we get. We would say we have some function of r1, since yc is same, is common from the two sides, so we can say We can ignore that yc. So I would write r1 divided by, so differentiation of that function with respect to differentiation of x with respect to z is 0, and we would say dz by so we can get finally minus 1 by x plus r2. From this side we can get L minus x divide, and we have from this one, this goes 0, this goes 0, this goes 0, and we differentiate with respect to z, so we got a positive value of 1 equals to 0. So that means r1 by x is equals to r2 by L minus x. Now, if I write it in terms of r1 by r2, or should I write it in the other way? Should I write it in this way or the other way? Now we should keep it as that of initial case. We should keep it in this way. That's your standard. That means some kilonewton per meter should be some kilonewton per meter. So that means average load, we say this one as average load. This is some loads. Average load on left of C should be equals to average load on right of C. So average load on left of C is equals to average load on right of C. But this thing seldom happens. If you have a different number of point loads, this is not happening every time. You take any problem, you would see that this thing that we derived, it is not going to happen each and every time, because your average load can be different. It's not necessary that it would be same always. It's not necessary that it would be same. Let's take any values, general values out of the mind, out of the box. You can take let's say that loads on this side was r1 was equals to 40 kilonewton, and the length was x equals to 5 meter. And let's say r2 was equals to r2, what we can say, summation of resultant of loads was such that it was equals to 43 kilonewton and length was 3 meter. So I would say 40 by 5 is equals to 43 by 3. That's not same. And similarly, I had ensured that r1 and r2 is such that its equation is equals to this. And if you try to ensure that also, you won't get that. I try to give you a brief that if you did that, r1 is such that you had some value, and you would still get some value of, let's say you get a value of some x, some value of a, and divided by some value of x was your length on the right side, on the left side, and you got some value of r2 equals to b for the length of L minus x, and you would still get you won't still get it equals to this one. Then we interpret this what we have this equation, or this general thing we have derived, that we interpret it in a different way. We interpret it in a different way. So where we got, so we got this one, that r1 by x equals to r2 by L minus x. So we do iterations of those different loads. So we don't know on what values of r1 and on what values of r2 your x is fixed, okay, and we say on what values of r1 and r2 by crossing those loads on the section C. So we try to move those loads. We try to move those loads one by one and try to see what's happening on the equation. What's happening on this equation? R1 by x. There would be some R1 firstly. Then you take one load out of that. You transfer it to the right side of section. You see what's happening on this equation. Is going here and there. Is going any oscillations to and fro. And if there is any sign change, if there is any change of sign of this equation, I would say if initially it was r1 by x was greater than r2 by L minus x, if it was initially greater, and on a particular load the sign got changed, we say, oh, this one is your critical load. Then we keep that critical load as the load on the section itself, and based on that one we get the maximum bending moment. Let's go for that one. Then so we interpret it in this equation in this way, that we write this seldom happens. This is not usually happening. This seldom happens. This is not always true. I would say this does not happen always. So for this one, we interpret it in this way, that we say you roll loads on C, then we say change of sign, that we can also show you later. Change of sign, that is your critical load. Then we keep that load at C. Keep that load, critical load, P critical at C. P critical at C. Then we can keep that also. Okay. So for that, let's go for the first problem. Let's go for the first problem we can have. Let's go for the first problem we can have. We can have the first problem that is saying we have that 4 loads. One is 10 kilonewton. Next one is that 15 kilonewton. Third is 15 kilonewton. Fourth is 8 kilonewton. And the spacing is that 2 meter, 2 meter, 2 meter. 1, 2, 3, 4. How much loads we have? 2, 2, 2. 2, 2, 2, 2. 10, 15, 15. I think we have 4 loads, yeah. The spacing between them is 2 meter each. And we have a girder of 30 meter. And your girder means assembly support beam. We can say a girder beam. This is a bigger beam. Girder beam of 30 meter. And we need to get the shear force at 8 meter. That means section C is at x equals to 8 and moment at 8 meter. Maximum. We want to get these values as maximum values. Shear at 8 meter and moment at 8 meter. Now let's make the shear force diagram, that ILD for shear force. We have 30 meter beam, simply support beam. We have some simply support beam, 30 meter, A, B. There is some section C at 8 meter. Let's say total is 30 meter. We have some section of C at 8 meter from support A, and we need to get for the point loads, we have 4 point loads, train of loads moving in the left to right direction. So the direction of movement is in this way. That means this is your leading load, and 8 kilonewton is your trailing load. We can keep that as trailing load. Okay. So we need to get the shear force V8 and M8. Let's go for the V8. If I make the ILD for shear force at C, can you draw that? I would say that would be in this way. Some 8 by L and some 22 by L. So this is your variation, positive, negative. This is negative, this is positive. So this value is 8 by 30. And remove now these things we can remove. 8 by 30, 8 by 30. And this part, top part is 22 by 30. 8 by 30, 22 by 30. Now, if you want to calculate V negative, maximum, we already told you that you perform trials for the shear force. You perform trials. First trial is that if you talk about the negative, we have this one for the length of 8 meter. We have this length of 8 meter total negative, and we have we have 4 loads, and total length of this is 2 plus 2 plus 2, so 6 meter. That means all 4 loads can be placed on that negative side. That means all 4 loads can be placed. Let's place them in such a way that all loads are on this side. So if I try to place that load 10 kilonewton, because we are moving in this way. So if I try to keep 10 kilonewton here, then after that 15 here, after that 15 here, after that 8 kilonewton here. So such that total is 8, and this is 2 plus 2 plus 2 plus 2, that is total of 8. So this is 2 meter, this is 2 meter, this is 2 meter, this is 2 meter. Then we need to get ordinates also. If this was your 8 by 30, and by the symmetrics, this would be your 6 by 30, this is your 4 by 30, this is your 2 by 30, and this is your 0 by 30. So we got these ordinates, kilonewton. Unit is in kilonewton. Now this is your first trial. You can say V negative. We can write V minus 1, V negative. First trial. I would write that is 10 into 8 by 30. We can keep the 30 outside because it's a common for all. I can keep 1 by 30 outside. I would write 10 into 8 plus 15 into 6 plus 15 into 4 plus 8 into 2. And it's all negative, so I have V1, that's minus times some 8.2 kilonewton. And if I apply one more trial, if I say maybe there might be chance that if this 10 kilonewton is, because it is having a low peak of less 10, if I keep 15 on this peak of negative Vmax, if I keep this 15 kilonewton on this side, I might get some maximum value. Let's check that trial also. Let's have that trial also. That means I try to have these loads in such a way that I try to move those in this fashion. Now I would say your 10 kilonewton is, because we are moving in this direction, so 10 kilonewton we are keeping here, 10 kilonewton on the positive side, then we are keeping 15 kilonewton on the peak ordinate of negative side, then similarly next to 15 kilonewton, and after that 8 kilonewton here. So our ordinates got, so for the 15 kilonewton our ordinates got increased, but you had one thing, that one of the loads is on the positive side, and we need to calculate this, that if this is 2 meter, we need to say if the ordinate on positive side is 22/30 for maximum, and after 2 meter we need to calculate this ordinate also. Can you calculate this ordinate? I would say total length is 22, and this smaller length would be 20. Can it? Would it be 20? This would be 20/30. So finally this ordinate would be 20/30. It is in this way, 22/30 for the length of 22, but I need for the length of 20. So this is 20/30, 2/3. 2/3. So I can have the ordinate of 2/3. Where the ordinate of 2/3 can have. So if I solve that, I can write V2 negative, that is equals to some 1/30 times, that's negative 1/30 times 15 into 8 plus 15 into 6 plus 8 into 4. You have these three loads. They are on the negative side, so I kept a negative. And for the fourth load that's on the positive side, I would write plus 10 into ordinate of 2/3. So I can have that value equals to 1.4 kilonewton. See, initially it was more value. Now it got reduced. Maybe it was minus 1.4. Maybe you can check that also. Minus 1.4 might be here. So you got lesser load. So you can take V negative maximum is equals to 8.2 kilonewton. Now, had this load been 150, there was a chance that you can keep this load on the other side. But the variation is not such. But overall, if you see, the value has decreased. Now let's go for the positive side. If you go for the positive side, we have these four loads, and let's calculate the ordinates. If this is 20/30, and after 2 meters we have 18/30. After 2 more meters we have 16/30. So these four we have to keep. So let's say that V1 positive would be equals to 8 into 2. 8 into, is it 2? No, 8 into 2. We have the 30 common, we can keep 30 outside. 1/30 plus 1/30 into 8 kilonewton into intensity of that ordinate of 22 divided by 30. So plus similarly 15 into 20 plus 15 into 18 plus 10 into 16. So you can get a value of V positive 1 equals to 16, 18, 20, 22. I think 30. I think this is 30.2 kilonewton. You check that also. 30.2 kilonewton. Now I think there we can apply one more trial, because your 8 kilonewton, we see this is on the peak ordinate of that positive shear force diagram, positive shear force that ILD. If I try to keep that 15 on the peak ordinate, I would try to see whether the value might get increased or not. So I would try to keep that in this way. So let's keep the loads now in this fashion. Let's remove the values. 8, this one is 10, and let's remove this arrow. So I would say 10 kilonewton is here, this is 15, this is also 15, and one load is on the negative side, that is having a peak of 8 kilonewton. So it would be acting at 2 meter here. We know that ordinate there would be 6/30. Ordinate there was 6/30 by the similar triangles. We already checked that also. 6/30 is there. Now we need to get the V positive. Let's write that V positive 2. V2 positive, and that would be equals to, and this one is negative, I would say minus 30 is 1/30 we can keep common. 1/30 we can keep common, and we can say 8 into 6. 8 into 6, that's negative. we can keep positive outside it. For this case, we can keep it negative. 8 into 6, because your peak ordinate is negative, I can say. And after that, we have positive values of 15 into 22 plus 15 into 22. Then after that, we have one more kilonewton, 15 kilonewton, 15 kilonewton into 20. Similarly, we have one more load of 10 into ordinate of 18 by 30. This is 10 kilonewton into ordinate of 18 by 30. Then 30 we have kept common. So finally we get V positive 2. V2 positive equals to 25.4 kilonewton. 25.4 kilonewton. So you got this one. And out of those ones, which one is the V positive maximum? So we got V negative maximum 1. We got this one, V positive maximum, V negative maximum. And from this one we can get, out of these two, we say this one is your V positive maximum. Now third thing is that get the moment at 8 meters as maximum. That means moment at C to be maximum for these train of loads. We saw that average load on left of C should be equals to average load on right of C. We derived that equation. We derived that condition that let's remove that first. I would say let's try to remove this one. Shear force is over. Shear force is over. We perform two trials. We perform two trials in this problem for each case. Usually you have to perform two trials. Okay. Then now we are going for the moment at C. We are going for the moment at C. Moment at C. Now, can you draw the moment at C diagram? Moment at C diagram. Moment at C. We have that moment at that total length of 30 meter. Total length of 30 meter. That A, B. Can you draw the that what you call as moment at C ILD? If the section is at 8 meter, so I would say AB by L. Can I say AB by L? I would say this is 8 meter and this is 8 meter, this is 22 meter. And the ordinate here is YC. YC equals to 8 into 22 by 30. And that we can calculate, that is equals to, let's have that value, that's equals to, I don't know, that you can say, that you can get the value of YC. So you got some value of YC. Value of YC, some meters. So you got the value of YC. Now I would say there we have some resultant of loads on this side R1, and we have from this side resultant of R2. Then we say R1 by X is equals to R2 by L minus X. Then we see the condition for that. But how do we solve actually this problem? How do we solve for this one? For moment at C to be maximum. Moment at C to be maximum. How do we solve for the moment? We say you do one thing, you roll the loads. So we say which load is crossing. We write it in this way. Which load is crossing that section C? Load crossing C. So we see which load is crossing. From our case is that we go from left to right. Then we say that what is the average load? What is the average load? Average load on left. And what's the average load on right? Then we'd say remark. We apply some remarks. Then we see whether the sign is going to change or not. So let's have that remarks also. So I would say firstly let's go for the, because we have four loads and the leading load is 10 kilonewton. Leading load is 10 kilonewton and your X value is 8 meter and L minus X is 22 meter. So this average load on left means R1 by X. R1 by X, and this one is R2 by L minus X. So we need to get that values also. So let's go for first one. Since we are going from left to right, so we take the load 1 as 10 kilonewton. So this is your first load, 10 kilonewton. 10 kilonewton. So I would say if this has crossed C, that means on the right, what should be the value of R2 by L minus X? I would say from the right side, the value of loads is only 10. That means 10 by 22. 10 by 22. And from this side, I would say total loads are, we have what is the total loads? We have 8 plus 15 plus 15 from the left side, that is 38. So I would write 38 by 8, 38 by x. So we see that remarks means that if I calculate this one, I can directly show that this value is greater than this one. That means remarks, that sign change. So we say this one or this one. Let me write here directly. Let me write that directly here. Now second load, if I transfer the second load to the right of that section C, if I transfer the next load, that means 15 load has crossed the section C. Section C is now here, and 15 load is now has crossed. That means the loads on the right would be 10 plus 15, that is 25 for this length of 22, and the loads on the left of that section C are now only 23 for the length of 8. And still we see that this ratio 23 by 8 is greater than 25 by 22. When if we write load 15 kilonewton was passing, first kilonewton 15, if the next 15 kilonewton is now passing, if this load is now crossing 15 kilonewton, so we see that your loads on the right side becomes 25 plus 15, that is 42. That's 25 plus 15, that's 40 for the length of 22. And we see from this side, what is the value here? We see that total loads on left are only equals to 8 kilonewton now for the length of 8. Now we see that there is a change of sign. We see that there is a change of sign here. That means when the second 15 kilonewton was on the section, there is a change of sign. So we write here change of sign. We can write here change of sign. Change of sign. If there is change of sign, I say place this load, place this second load, second 15 kilonewton load on the section itself, on the section C itself. So if I had that diagram, I would say, if this was your diagram, let's remove R1, R2. Let's remove this R1, R2. I would place only the loads now, actual loads. I would place only the actual loads now. I would say, place the load R2, place the load that was your second 15 kilonewton. One of the 15 kilonewton has already crossed that section C, 15 kilonewton. And there is one more load of 10. And from this side, there is only one load of 8 kilonewton. And now we need to get the ordinates also. So this was your ordinate of YC. This would be ordinate of YC for 6 by 8, because it was for the length of 8, I need for the 6 meter. This was for 8 meter, I need for 6 meter. Similarly, from the other side, this ordinate was YC. This was YC for the length of 22, but I need for 20. And this ordinate here would be equals to YC for the 18 by 22. So I got the ordinates and I multiply them with the loads, and I can get the total moment at C to be maximum. So then MC is equals to, let's go for the 8 kilonewton into that ordinate of 6 by 8 meter. YC we can keep common. Plus you can write next to load of 15 kilonewton. 15 kilonewton into 1, because YC is we are going to keep that outside. So 15 into 1 plus 15 into 20 by 22 plus 10 by that 10 into 18 by 22. 10 into 18 by 22. That multiply of YC. So already we have multiplied that YC equals to some value, and you can get the final value of moment equals to 251.21 kilonewton meter. I hope that you got the problem, that what we are doing. So I hope that you got that. Let's take another problem we can have. Let's go for another problem we can take. Okay. So we have 5-point loads. We have 5-point loads acting here. 40 kilonewton, 50 kilonewton, 60, 60, and 20. Spacing is at 1.5, 1.5, 2 meter, 1 meter. Okay. Now the length is that we have total length of 15, and section C is 4 meter is at 4 meter from support A. So this is your section. That means this is 4 meter and this is 11 meter. And section C is here. And we need to say maximum shear force at C and maximum bending moment at C. And let's go for the shear force at C. I would draw the shear that ILD for shear force diagram for the shear force. Sorry, ILD for shear force at C would be in this fashion, and this would be your 4 by 15. This would be your 11 by 15, negative, positive. And now for the V negative, and I can clearly say that V negative would be lesser because your area is lesser. I can say your area would be lesser. If I still calculate that negative value, I would see how much is the length of that D. I would say it's having total length of 3 plus 2 plus 1. That is 6 meter. 6 meter length, but your section, but your X is only 4 meter. That means it will only take few loads here. Let's keep the maximum loads we can have. Let's say that 40 kilonewton is here. After that we have some 50 kilonewton. After that there might be one more load of 60 kilonewton here. So this is the possibility: 40, 50 and 60. Now because of that, I would say you would have some value of ordinate 4 by 15, and you can get this value as total length is 4. You subtract that, total length is 4 meter. This is total of 4 meter. And if you go 1 meter to the left side, we'd say this is total 3 meter triangle. So we write 3 by 15. This one would be your 1 by 15. And you can get the V negative. That would be lesser with respect to V positive. V negative would be equal to 40 4 by 15 plus 50 3 by 15 plus 60 into 1 by 15. So this is your all negative. So finally we can get a negative value of V1 negative that equals to that comes out to be equals to 40 into 4 by 15, 50 into 3 by 15, 60 into 1 by 15, 24.667 kilonewton negative. And one more case you can take. If you say that 40 kilonewton is lesser, it is lesser, you can take that 40 kilonewton outside. That means it can keep that on the positive side. And now for the 4 meter we have this 4 meter, and you can keep that 50 on this top and 40 kilonewton outside and 60 somewhere here. And you would see how many loads we can have after that 50. Would say this is 2 meter and this is 3.5, and 4 meter would be somewhere here. That means this load won't be anywhere. This would be outside that section. If I take that 60 is here, one more 60 is here, then I can get the ordinates also. Ordinates, you can calculate those ordinates. This one would be 0.5 by 15. This would be 2 by 15, and this we already know. And you calculate for that condition also. And corresponding to this 40, we have ordinate of 11 by 15 into 10 by 11. So 10 by 15. And you calculate that also V2. That's also negative. So you would get a value of minus 14.67 kilonewton. But that means your value of this one is your absolute, or not absolute, we say this is your maximum negative shear force maximum at point C, at section C. Now we'll directly say that that shear force is maximum on the positive side. Positive side we can have shear force maximum. If we take this side and we have these 5 loads, we have these 5 loads, let's go for these 5 loads. So we have these 5 loads acting here. If I take that, they are moving in the left to right direction. Now the thing is that which of the loads you would try to prefer on the peak. If you try to peak, take 20 kilonewton here, 60 here, 60 here, 50 here, and 40 here. Total length of the loads is 2 plus 1 3, 3 plus 3 is 6 meter. Total length is 6 meter. We have 11 meter here at bottom. So this length of 11 meter. That means you can get the ordinates also. This is 20, and then after that we have 9.5 by 15. This one would be 9.5 minus 1.5, that is 8 by 15. And this ordinate, we have to subtract that. 8 minus 2, that is 6 by 15. And this one, by the similar triangles, you can do that. And finally, you have 40. And this one is your 5 by 15. This one is your 5 by 15. 5 by 15. Now we can get the value that V positive would be equals to, that would be equals to, apply those values, 20 into, let's keep the 1 by 15 outside. I would say 20 into 11 plus 60 into 9.5 plus 60 into 8 plus 50 into 6 plus 40 into 5, and equals to some value of 1 to 1. Yeah, this is 118 kilonewton. So you got this value. Let's write this as V positive C1. Now we'll take one more trial. Because we kept the load, that's 20 kilonewton. We kept the 20 kilonewton at the peak. Now if we say let's don't keep that on the peak, let's try to keep this 60, because this is the maximum out of these. Let's try to keep this one on the peak. So let's try to keep that 20 on the peak. So let's try to keep that 60 on the peak. Let's try to keep that 60 on the peak. Let's try to keep that 60 on the peak. So let's try to keep that 60 on the peak. That means your 20 kilonewton would be on the left side of the section. Won't be there. So I would say your 20 kilonewton would be here. 20 kilonewton would be here. 60 would be on the peak. And next to 60 would be here. And 50 would be here. 50 would be here. And 40 would be here. Now, corresponding to this, there would be some ordinate here. I can say, what is the ordinate here? Can you tell me? For the 4 meter length, we have 4 by 15 here. And for the length of this triangle, this is 4 minus 1.5, that is 2.5 by 15. This ordinate is minus 2.5 by 15, and you can multiply that. So if I now calculate that, V positive 2 at C, that is equals to minus times 20 into 2.5, and keep that, if I keep that 15 outside, I can say this is your minus 20 into 2.5. Then after that, we have 60 into ordinate of this maximum ordinate was your B by L, that was B by L, 11 by 15 plus, yeah, 15 we keep outside. Then third one is that 60 into 9.5, 60 into 9.5 plus, after that we have, but the ordinates would get changed because your value of Y, because your distance is also changing. 1.5, 1.5, 2, and 1. We need to get the ordinates now. We need to get the ordinates corresponding to these. We need to get the ordinates. So I would say the maximum ordinate we have this one, 11 by 15. After that, the distance between 60 and 60, that is 2 meter. That means this ordinate would be 9 by 15, because 11 minus 2 is 9. So 9 by 15. Accordingly, that 50 kilonewton, yeah, actually this is 9.5, because distance between 60 and 60, that's 1.5. 1.5. So you write 11 minus 1.5, that is 10, that's 9.5. 9.5 by 15. And this one would be 9.5 minus 2. 9.5 minus 2, that's 7.5 divided by 15. And this ordinate would be 7.5 minus 1, that is 6.5 divided by 15. So you have these ordinates and you multiply with the load. You multiply the ordinates with the load. So 60 into 9.5. And after that, we have that 50 into 7.5 plus 40 into 6.5. And you solve that, well, that one also, and you have that shear force, shear at C, that's positive, and that is equals to 1 to 1 kilonewton. Now if I compare that with the first one, initially we say that initially was 118, and second one is your V, we can say this is your V positive maximum. In this case, initially we said that let's keep the 20 kilonewton on the top. Because of that, we got this one. And even now in the second case, even we kept one of the loads on the negative side, but because the 60 kilonewton was a bigger value here, its effect was such that the overall velocity we got increased by 3 units. So there we have performed 2 trials. Now for the moment at C to be maximum, I would say for the calculation of moment at C. Now for the calculation of moment at C, let's go for that. Calculation for moment at C. Calculation for moment at C. Calculation for moment at C. Should we go for that? Let's go for that. Calculation for moment at C. I would say your section is here somewhere, and it's having an ordinate of YC. This is ordinate of YC. I would say what's the value of YC? That's AB by L. Is it 4 into 9? 4 into 11. 4 into 11 by 15. AB by L. That's the ordinate of, you might have checked that. AB by L equals to 4 into 11 by 15. Let's keep it as it is. So you can calculate that, 44 by 15. And that ordinate is here at the section C. Now we know that how to solve that. For the moment at C to be maximum, we say that average load on the left is equals to average load on the right. But that's not always happening. So we say you cross the loads on the section C, then we see that where is the change of sign, on what particular load there is change of sign. So let's write that. Let's write that now. So we say your length is 4 meters from this side and 11 meters from this side. Let's write that load crossing. Let's write load crossing C. Which load is crossing C? Then we write average load on left and on right. Then we can write remarks. Let's keep that remarks outside. I would say first of the load, we are going left to right. So first load, when you cross 40 kilonewton on the section, that means it crosses, first load is 40 kilonewton, it crosses the section C. So for that condition we say, your loads on the left, loads on the right would have been only 40 and divided by length of 11. And the total loads on the left would be equals to 20 plus 60 plus 60 plus 50. That is 190, I think. 190 for the length of 4. And I can say this is greater. And when the load 2 is crossing, load 2 is that 50 kilonewton. When the 50 kilonewton is crossing, I would say total loads on the right would be 50 plus 40, that's 90 for the length of 11. And from this side we have subtracted that 50, so I would get 140 by 4. And this still is greater than that, left is greater than right. Now second load, when we have this 60 kilonewton passing, I would say from this side we have 90 plus 60, that is 150 kilonewton loads per 11 meter. And from this side we have only 80 by 4. And I think that is still greater. This is 4, this is 20 times. That is still greater. Now if we take one more load, that second 60 kilonewton, I would say from this side we have total load of 150 plus 60, that's 210 for the length of 11. And from the side we have only 20 kilonewton for the length of 4. And after that we still see that this is your 11, this is your 2 Pfizer. So I think this is the change of sign. Is there any change of sign here? If I say what is 20 by 4, that's 5. 20 by 4 is 5. And from this side 210 by 11, this is 19. What's the value of 80 by 4? What is the value of 80 by 4? Can you calculate? 80 by 4 is 20. So if I write that, this value is equals to 20. This is 20. And from the side 50, 150 by 11, what was this value? This was 13.6. This was 13.6. So for now this case, 20 by 4, that is equals to 5. And what is this value? 210 by 11, that value is equals to 19. Now can you see the change of sign? Can you see the change of sign? Can you see the change of sign here? I think there is a change of sign at this particular load of second 60 kilonewton, we can say. So there is a change of sign. On this change of sign, on this load, there is a change of sign. So we can say your second 60 kilonewton load is your critical load. So you have to keep this load on the section itself. So let's keep this load on the section itself. So this is your 60, and on this side, at a distance of 1.5, we have this 20 kilonewton now. And from the other side, we say at a distance of 1.5, we have one more 60. After then we have 2 meters, then we have 50 kilonewton, and after 1 meter we have 40 kilonewton. Now we need to get those ordinates and then multiply them with that load, and you can get the moment at C to be maximum. Now by the similar triangles I can get those ordinates also. So the lengths we have, this is your 1.5, this is your 1.5 meter, this is also 1.5 meter, this is 2 meter, this is 1 meter, and now I can solve that also. So the ordinate at the C is YC. YC is the ordinate at C. So this one would be this ordinate would be equals to YC 2.5 by 4. Can I say that YC was for this 4 meter, but I need for 2.5 meter, and this ordinate would be this ordinate was YC. It was for the length of 11, YC for 11, but I need for 1.5 minus 11, that is 9.5, and this one would be 9.5 minus 7.5, so 7.5 by 11 YC, and this one would be 7.5, this is 6.5 by 11 YC. So these we have the ordinates, we have these ordinates. Then we can write moment at C would be equals to 20 into 2.5 by 4 plus YC we can keep outside. The value of YC already we know that we can calculate. YC already we know, then we write 20 into 2.5 by 4, then 60 into 1, 60 into YC, plus then after that 60 into 9.5 by 11, then plus 50 into 7.5 by 11, then plus 40 into 6.5 by 11. Then you calculate that and you would get a moment C equals to 534 kilonewton meter. Now the thing is that let's go for one more problem. So it's saying that we have a span bridge girder. Next problem is that we have a bridge girder of 25 meter span. There is a span 25 meter, and we need to get the bending moment at section that's 10 meter. So here we have some section at 10 meters. So C is at 10 meters and this part is your 15 meter, and we need to get the bending moment at C. Now we have the loads. That's 1 2 3 4 5. So the loads are in this fashion: 200. After that we have one more 200. After that we have 200. Then we have one more 200. Then after that we have 100. So these loads we have, they are kilonewton. So these loads we have, and the spacing between them is 4 meter, 2.5 meter, 2.5 meter, 2.5 meter. Now it's saying that the problem is the difference in the previous problem and this one is that that this series of loads, they can cross either of the direction, cross in either of the direction. So we need to check for left to right condition and right to left condition. So we have two conditions for this one. So we need to check for the both conditions. But the section is fixed. That section at C is at a distance of x equals to 10 meter from A. For that condition, we need to get the bending moment at C to be maximum. For the two cases when load was moving from left to right, and for the second case when load was moving from right to left. So let's go for our conventional case, that is left to right. Let's take the first case that the loads are going from left to right, but which one is leading? It's mentioned that whichever way you go, your 100 kilonewton is leading. This is leading always, right? This one is leading always. That means for the first case you have to go in this way, that 100 is first, after that 200, 200, 200, 200. So if I draw the BMD for this one, can you get the ILD for the BMD? Sorry, not BMD, ILD for the bending moment at C. We are always used with that BMD SFD, so that's why it comes to our mouth. So let's write that. This one. So I'd say, this one is your that YC would be here. YC equals to 10 into 15 by 15. Sorry, 10 into 15 by 25. 150 by 25, that is 6 meter. So ordinate of 6 meter is equals to YC. Yeah, YC equals to 6 meter. Now I would say for the first case, let's roll the loads. We know that we have that average load on left is equals to average load on right, and for that case we say you cross the loads on the section C. So let's cross the loads. I would say load crossing C, then we have average load on we can write left and right, then we can finally apply remarks. I would say let's keep the first load, that is 100 kilonewton, because the leading load is always 100 kilonewton. So for the left to right condition, this is the case one, that we are going from left to right condition. So 100 kilonewton is the first one, leading one, 100. So I would write that in this side we have 100 for the length of 15, and on the other side we have 2 to 4 to 8 to 6 4 8 800 kilonewton for the length of 10. And similarly, next load, let's go for the next load, that is 200. I would say from this side we have 300 by 15, and from this side we have 600 by 10. Let's go for the third load. Third load is also 200. So I would say from this side we have some loads of 500 by 15, and from this side we have some loads of 400 by 10. So let's go for one more load, then I can show you that finally. Let's go for one more load. That's 200. This one 200, and here we have 700 by 15, and from this side we have 200 by 10. So let's see that where on what particular load your change of sign was there. So I would say this one is greater, this one is also greater, this is 4, this is 3, so this is also greater, and on this I think on this side this value is 40, and 500 by 15, what is this value? 500 by 15, 3.3. This one is 40. 400 by 10 is 40. Yeah, there is no change, and it's still greater. And for the last case you have 200 by 10, that's 20, and from this side we have 700 by 15, so that value is 46. So I would say on this case, when this load was crossing C, we had the change of sign. Okay, right, the change of sign, I would say this load is critical. So this is critical. So third 200 kilonewton load is critical. That means on the load where I applied that tick, that is your what you call as critical load. So you have to place that critical load on the section itself. So this is your 200, and that means there is only one load after that, so that's 200 from this side, and all other loads have to be placed from this side. 200, and we have 4 loads of 200, so one more 200 is there, and after that we have 100. Then we need to get those ordinates. We need to get those ordinates now. So I would say this is your 4 meter, this one is your 2.5, this is 2.5, this is 2.5. Can I get the ordinates? I would say the ordinate here is 0.75 of YC. This is 7.5 by 10 of YC. And from the side, I would say the total length is 15, and it was YC for the 15. I would say this is your 12.5 by 15 of YC, and this one would be equals to 10 by 15 of YC, and this one would be 6 by 15 of YC. You can do that by your similar triangles. 6 by 15 of YC, and you can get already YC, so you can get the M at C when we go from left to right. So you can write this is your case 1, so you can calculate that 200 into 0.75 of YC. Let's keep the YC outside. 200 into 0.75 plus 200 into 1 plus 200 into 12.5 by 15. Then we have plus 200 into that 200 into 10 by 15 plus 100 into 6 by 15. Then times YC. So finally you can get value of MC left to right equals to 4140 kilonewton meter. Now next case is that we go from right to left. Let's go from right to left. Now second case is that we go from right to left. So next case is that we go from right to left. So your loads are moving in this direction now. That's your 100 is first. After that your 200, then after that 200, then after that 200. So if I write the second case, case B, right to left, loads are moving in this direction. So let's write those values now. So I would calculate those values now again. So initially there was no load on the right side, the left side of section. All the loads were on the right side. Now once one of the loads, that's the leading load 100, gets transferred to the left side. So I would write that now. One of the first load gets transferred to the that what you have left side of that section. So I would say your intents here the value would be 100 for the length of 10, because your section is at 10 meters. So 100 for the length of 10, and from the other side we have total loads of 2 2s or 4 2s or 800 by what you have 15 meter. And for the second load, when you transfer it, the loads on the left would be equals to 300 by 10, and from this side we have 600 by 15. Similarly, for the second load we have 500 by 10, and from this side we have 400 by 15. And for the last case, and when the last load of the 200, that is the third load, if we transfer this one, we have 700 by 10, and from this side we have 200 by 15. If we see why is the change of sign, I would say this is greater. This is 30 by 10, this is 30, and this one is 40. 600 by 15, what is this value? 600 by 15. That's 40. Yeah. 100 by 10 is 10, okay, but 800 by 15 is greater. So that means 53. So the direction is not correct. So direction should be in this way. This is also greater. And 400 by 15, if you say what is this value, it's 26.6, and from the side we have 50. So we can see that this value is equals to 26.6, and this value is equals to 50. So I would say there is a change of sign here. There is a change of sign on this value of 200, on third value, change of sign. So the change of sign, we can say we have one statement that on the change of sign, that average load on we can say right to the average load on left, we say that we also call it as the critical load is 1. P is critical if change of heavier side goes to heavier side changes to what you can call lighter side, and vice versa. That means your heavier side becomes lighter and lighter side becomes heavier, because we have change of sign of that average load. Then accordingly we can say your second 200 kilonewton is critical here. So we are going from right to left, so we have to keep that two loads we have to keep on left side, and this one on the peak ordinate, and this one, and one more 200 was there, that we have to keep on the right side. So for that, let's have that ILD again. Let's make the ILD again. Peak ordinate, we already know that was your 6 times, that was your 6 meter. So we would say this is your YC, and on this point we had to apply which 200? Second one. So this one is your second 200. That means there should be one more 200 here, and there should be one more load, that was your initial load of leading load of 100. And after that we have 2 more loads of 200 from this side. Now the length here is 4 meter, and all other are 2.5. Now we need to get the ordinates. This was your 10 meter length, this was your 15 meter length, and we can say by the symmetry, by the similar triangles, we can calculate those ordinates. This one, here, and here. I would say this is YC, and this one would be, YC was for 15. I would say this one is your 12.5 by 15 of YC, and similarly this one is 10 by 15 of YC. And from the side we had 10 meter total length. YC was for 10, I need for 7.5. This one is your 7.5 by 10 of YC. And this one is your 7.5 minus 4, that is 3.5 by 10 of YC. Yeah. Let's write the values now. Calculate moment at C for the second case. For the second case, I would say 100 into 0.35. Let's keep the YC outside, so I would write 100 into 0.35 plus 200 into 0.75, 7.5 by 10. After that, we have third load. We have third load of 200 kilonewton into ordinate of YC. Then we have 200 into 12.5 by 15. After that, we have final one, 200 into 10 by 15. And whole multiply, we have YC. So we can have, finally we can write that equals to 41.10 kilonewton meter. Initial value was 4140, and this one is 4110. So sorry, difference we can have. So this second case is greater, so this one is your M max. We can write M max at C. For the second case, when loads were going from right to left, so at that case we have maximum bending moment by some amount, that is 30 kilonewton is more in the second case. For the second case, we have second. So we got this one also, 60, 20, 60, 40. We are left with how much problems we have? 1, 2. So I think we should take a break. We should take a break now. Let's take one more problem. Let's take one more problem, then we would see. Let's take one more problem. So it's saying that you need to get the maximum shear force bending moment. Shear force bending moment at quarter span. At quarter span. That's at L by 4 from support A. At L by 4 from support A. If the total length is 3 plus 9, that's 12. That means 3 meter, 9 meter. This is your C point, quarter span. Simply support beam. 12 meters simply support beam, and with the UDL length D greater than the span length, So okay, no problem. Okay, no problem with that. UDL is having intensity 20 kilonewton per meter, and there's one more load. That's your point load. That's point load. P equals to 100 kilonewton, and it can occupy any location, can occupy any position. It occupies any position. It can occupy any position, and we need to get the maximum shear force at section C, bending moment at section C. That's at quarter span. So if I draw that ILD for shear force at C, I would say the variation would be in this fashion. Let's make by straight lines. This is your negative, positive, and the ordinates would be 3 by 12. That's 0.25. This would be 0.75. So we got the ILD for shear force at C. Then for the positive, if I directly write now, for the negative we can ignore, or if we want to write the negative, if you want to write for the negative, we have the ordinate of 0.25 and length was 3 meter, and you can keep the UDL for this part only. You can keep the UDL for this part only, and you apply the point load at the peak ordinate. So you can get the values that what is the V negative maximum. We can say that is 1 by 2 area of the triangle into UDL intensity was 20 kilonewton per meter, and you can then plus because of the effect of concentrated load P, your load was P equals to 100 kilonewton, and ordinate at that point is 0.25. So you can get V negative maximum, that is 32.5 kilonewton. Now similarly, you can write V negative maximum, V positive maximum. So for the V positive maximum, apply the UDL on this positive side, and a peak load, concentrated load on the peak ordinate P. So I can say your load of 100 kilonewton into ordinate of 0.75 plus UDL, area of the UDL area under the UDL, area of ILD under the UDL 1 by 2, ordinate of 0.5, length of what you have 9 meter, and intensity of 20 kilonewton per meter. So you can get the V positive at C maximum equals to 142.5. So you can clearly see the difference, 142, and initially it was negative 32.5. Now the third is that for bending moment at C, bending moment at that quarter span. Bending moment at C, that means at the quarter span. So let's draw that IID for BMD at C. So that would be in this fashion. I know the value of YC. Do I know the value of YC? That's AB by L. That's AB by L, 27 by 12, 27 by 12, 27 by 12. So I would say for the YC to be maximum, you apply point load. If I study that first case of when we studied effect of moving load, when there was only one load, we said that for the moment at section C to be maximum, you apply the load at that ordinate itself, because ordinate at that point is maximum, so you apply load at that point. So for that concentrated point load, we apply the load on this ordinate itself, on this section itself. So this is your P. And now for the UDL, but the UDL is having length greater than the span length, so we don't have to go with that D by L equals to D by so we know that equation, that Z by D equals to X by L. This is valid for when your UDL length is lesser than the span length. But this question is saying that UDL length is more, it's more than the span length. That means you can have UDL for the entire length. You can have the UDL for the entire length, because all diagram is positive, so you can apply moment. You can apply UDL for the entire length. So that means moment moment maximum at C positive equals to 1 by 2 area of the curve 1 by 2 into a length of 9 plus 3, 12 meter. Ordinate of maximum YC, this is also meters. Then you apply UDL of, how much UDL was there? 20 kilonewton per meter. Then we have that effect of concentrated load, 100 kilonewton into ordinate of 27 by 12 meters. So you can have moment equals to 495 kilonewton meter. So let's go for one more. And now the case is that we are talking about that train of point loads. So in the train of point loads, we covered that shear force at C to be maximum, bending moment at C to be maximum. Now we want to say absolute maximum shear force. So for that I would say you have that diagram positive. If you're talking about positive diagram, then we already tackled that. I think you apply that a large number of loads should be on this side, and you do some trials, and accordingly you can have maximum positive shear force, absolute. And accordingly you say you apply some trials for the negative side also. So C, option C is also done. Now part D, that is we have maximum bending moment under a load, particular load. Now let's say particular load is P2. We want to say what is the bending moment, what is the maximum bending moment we can have under a particular load P2. So this is the case 4 of that train of wheel loads for that condition, when we have that effect of that moving loads on that bending moment and shear force. So for this case we say what is the bending moment under a point load, under a specific load. So we say let there are some loads. So this is the whole of that problem. Let there are some loads P1, P2, P3, P4, P1, P2, P3, P4, P5. Let's say there are some loads P1, P2, P3, P4, P5, and we say our condition is that we specify our condition that we want, let's say we want maximum bending moment under point load P2, maximum bending moment under P2. We want this one. If this is my condition, if this is my condition required, if I say that I require this condition, this is my condition required, then I would say then consider the P2. Let's say this is P4, P3. Let's say this is P3, P4, and this one is P2. This one is P1. I would say this is the P2, and I would calculate the resultant of those loads. I will calculate the resultant. Let's say the resultant of the loads. Let's say this is the resultant of the loads, and I would say the resultant of the loads is at a distance of D from the considered load P2. So this is the distance of the D, resultant of the loads from the point load D. Now the thing is that condition for moment to be maximum under P2 is required. then we say resultant is R, it's at a distance of D from P2. Then we make the Mahol, then we make the Mahol that you apply the resultant at X. So we then design it in this way. Let's say that we have the resultant of all those loads. It's at a resultant of loads. Is at a distance of X, and we say the P2 was the distance was for the P2. It was some at a distance of small d. There was some P2 here. Okay, and we want to say on that under that particular load. That means our section has. So section was confined to point load P2. Once we got the value of X, once we got the value of R, then we'll say that this value of R is at a distance of X, and you add that plus D, then our concentric section C becomes this one. So under this load point P2, we want to say what is the value of bending moment here. So I would say you can get the reaction. If you got the reaction here, is R times L minus X by L. And if you calculate the summation of moments about this section, here the moments would be MC. I would say that equals to R times L minus X by L into length of X plus D. And your resultant is opposite direction. So I would write R times D. Yeah, minus RD. Yeah, minus RD minus R into D. That is equals to moment at C. So this thing I want to maximize. I want to maximize this thing. So let's maximize. It should be maximum to be maximum. Then we differentiate it with respect to X. Then we say dmc by dx equals to 0. Then from that we get a result of that X equals to L by 2 minus D by 2. So we say that. So the condition is that. Let me revise that. You have this simply support beam. Now the case was we want to find bending moment to be maximum under a point load, under any point load P2 to be maximum. This was our condition. Then we say that there was some resultant of those loads. At a distance of at some distance of X. I don't know the value of X. At some value of X. Then I said I already made them a whole that resultant and that particular load P2 was at a distance of X. Then I said I want bending moment under P2 to be maximum. At this location I want that moment at C. Now this is our C now. So moment at C to be maximum. That's our moment at under point load to be maximum. Then we differentiate it with respect to your X. Then we got the condition that the value of X should be such that it is equals to L by 2 minus D by 2. That means what's L by 2? What's actually L by 2? So it's if I try to have that on the beam itself, if I say the value of L2, what's the value of L by 2? Let's make that diagram. That if I draw that diagram. So if this is your simply support beam, and the midspan would be somewhere here, and this one is your L by 2. Okay, this one is your L by 2. And the problem is saying your resultant is at X equals to L by 2 minus D by 2. So your resultant is somewhere here. Let me have that. So resultant is somewhere here. This is your resultant, and it is at a distance of X equals to L by 2 minus some D by 2. And I know that from R to some what we have, some point load P2, some concentrated load P2. This was your section C. I would say this was your D by D. So then we say, can you tell me what is this value? Is it D by 2? And what is this value? Is it also D by 2? So what is the conclusion we can have? That if this was your center, of the beam, midspan you can write. If this was the center or midspan, that means to make the conclusion here, I would say for the moment under point load P2 to be maximum, or we can say Pi, that's your concerned moment load to be maximum, your resultant and Pi are equally spaced from, or equally distant, or equidistant from center. Can we say that? Because both are at a distance of d/2 from center. So your equidistant means they are at a distance of d/2 from the center. Can we say that from this one? Can we say that from this one? d/2. I think so. So we have 1, 2, 3. We can pause the problem. We can pause the lecture now. I think so. We can pause the lecture. Let's go for this next part. That's part E. So we say, let's go for the part E. When we call this part as absolute maximum bending moment. So absolute maximum bending moment when there are train of loads. We say when there are train of wheel loads. So this is the last case of this. This is the last section of this case D. We need to get this one. So usually we say near the midspan we have ordinate of YC, that is maximum. YC is maximum at what you call as at the midspan, and we also saw that if there was some concentrated load P2, the resultant was at a distance of D, and they were placed at such that both are at equally distant, equally spaced from what you call as from the midspan. So similarly, if you want that absolute bending maximum, if you want that, I want absolute maximum bending moment. So there is a possibility that it would be near the midspan. So we try to keep that. And if it is near the midspan, one more thing is that the maximum ordinate would be, maximum value of bending moment would be also when one of the load I would say one of the heavier loads would be at the ordinate, at this ordinate where we say your bending moment can be maximum. At that section we have to keep one load we have to keep at that section where we think that there's a possibility of bending moment to be maximum. Now for that we want to check that also. So there might be chances of that two trials can be possible. So one critical note we can have that we would get, how do we get this? So firstly we say there are n number of loads. Let's say there are P1, P2, P3, P4 and n number of loads. So the first step is that you calculate the resultant of that. What is the resultant of those loads from either of the side? Let's say the resultant of those loads is at R from this line. Let's say the resultant is R, and the that centroid is here. From this side we are calculating that centroid is X bar. So once we got that X bar, we would say now we might have, so the resultant would be somewhere between two loads. So one load is this one and second one is this one. So we would see what is the minimum value of that D, which was that between that constant load P2 and between that resultant R, which we call it that D. So we need to calculate that what is the D minimum we can have. Out of these two, we see which one is D minimum, and one more thing we have to keep, which is the maximum load out of these, P maximum out of these two. So we have to see where the resultant is. After that we have to compare out of these two loads which one is maximum and what is the minimum, that D minimum. So based on that, there's a chance that one or two trials are needed, and usually we say only one trial is needed. Let's go for this problem and we can understand what's going on. Let's take one of the problems. We say, let's say we have this problem. that we have simply support beam, and we have 4 loads. One is 80, then one is 60, 80, 100 kilonewton, and they are acting in this fashion. They are acting in this fashion. Distance between them is 2 meter, 2 meter, 3 meter. They are moving from left to right on the beam of 18 meter. Beam of 18 meter. This is a beam of 18 meter. And we need to get the shear maps, absolute shear and maximum absolute bending moment and absolute shear force. We need to get these two values, that what's the absolute shear we can have and what is the absolute bending moment we can have. For the shear force, we know when the shear force is absolute, that means when x is either 0 or when x is equals to L. So we can get either negative absolute value of shear or positive value of shear. So for the when x is equals to 0, so the diagram would be in this fashion. So one of the diagram would be in this fashion. This is +1 shear, and accordingly negative shear diagram would be in this way. This is -1. Then accordingly you place the loads, and you can do iterations also. You can do trials also. Let's place the load. Let's say this is our 100 kilonewton at the ordinate peak ordinate, and after that we have 80. After that we have 60. After that we have 80. So total length is 3 plus 2. That is 3 2 are 3 5 7. So 7, and total length of the beam is 18 meters. So I would say the theta here equals to 1 by 18. 1 for the length of 18. 1 unit for the per unit 18 length. So I would say, what's the V net, V absolute negative we can have? Can you calculate that? So I would say that is equals to 100 into 1. Then after that plus 80 into the ordinate here. That is the distance between them is 3 meters. So you subtract out of that 18, we subtract that. So we are left with 15 by 18. Then plus third one is that 60, and it's acting after the distance of 5. 18 minus 5, that's we can write 18 minus 5, that is 13 by 18. And for last load is acting 80 kilonewton at the length of 3 plus 2 plus 5, that is 7. That means 18 minus 7, that is 11 by 18. So you have that V negative, you can say this value is equals to 256.67 kilonewton. And second is that if you calculate that V positive max, V absolute but the positive value, I would say you place the loads in this way, that 100 kilonewton. So you can place 80 first, then after that 60, 80, 100. 80 kilonewton. After that you place 60 kilonewton, but then after that you place 180. After that we have 100. So accordingly we can have ordinates also. So this length is 3 meter. This length is 2 2. So we have these 2 meters. This is 2 meter, this is 2 meter, and this one is 3 meter. And how can you get their values? I would say you have this length of, we have this theta of 1 by 18, and this ordinate would be equals to, you subtract that 18 minus 2, that is 16 by 18, and this ordinate would be 14 by 18, and this ordinate would be 11 by 18. So you get that V positive absolute is equals to 80 into 1 plus 60 into 16 by 18 plus 80 into 14 by 18 plus 100 into 11 by 18, and you have to get a value of, you got a value of what you call as you get a value of 258.9 kilonewton. Now you might think that 80 kilonewton is lesser. If you want to keep that 60 on that part, and you would still get that you would still get lesser value. If you keep that 60 here, 80 here, and 100 here, and that 80 is outside the beam. If the 80 is outside the beam, you calculate for these three loads, and you would get a value of 203 kilonewton V positive. So I would say the V positive absolute would be that 258.9 kilonewton. This is our V absolute, that maximum absolute shear we can have. Now for the moment, this is our main part of the problem. Is that you calculate that absolute bending moment for this problem. One was your bending moment at particular C, when there was train of loads, when there was train of V loads. One was the problem of moment at C to be maximum. then we say that average load on right should be average equals to average load on left. Then we say that load is crossing that, we check the which one load is crossing. Then after that we say change of sign of that heavier to lighter. When there is change of sign, then we say that we keep on that particular section. But for the absolute bending moment, we would say we have to calculate that resultant of the loads. For the entire loads, we have to calculate where is the resultant of those loads. So let's calculate the resultant of those loads. Let's calculate the resultant of those loads. So that we call as absolute moment, bending moment. So let's get the CG of the loads. Let's get the CG of the loads. Can you calculate the CG of the loads? Let's say we calculate from this side, from the right side. Let's say we go from this side. I would go for the X bar. That would be that A1 Y1 by summation of AI. Similarly, this one would be PI XI divided by summation of PI. So let's go for that. I would write 100 into 0 plus 80 into 3, 80 into 3 plus 60 into 5 plus what you call as 80 into 7 divided by total loads. 100 plus 80 plus 60 plus 100, 80. So you would get a value of X bar equals to 3.4375. 3.4375 meter. That means after 3.4375, that means this is the centroid. This is the resultant of those loads R. That means R equals to this one. Now I would say out of these two loads between the R, out of these two loads 60 and 80, which one is maximum? I can directly confirm two things, that T minimum is also on the 80 kilonewton side, and one more thing, that 80 kilonewton load is also maximum. So I can directly say, I don't have to go for two iterations. I can directly say that maximum bending moment would be if the load is placed at an ordinate where you have to keep that 80 kilonewton. So I would see that, I'm going to see that now. So I would say you have this what you call as D minimum. What is the value of D minimum? If the total was from this side to this point, it was 3.4375, but after this one it was 3 meter. So that means the D minimum would be, this is your D minimum, that is equals to 0.4375. 0.4375. But we know one thing, that if I want that maximum bending moment, if I want absolute bending moment, I had to place the loads that in a way that your resultant, I had to place the loads in a way that your resultant and your concerned load, for that case, for our case, we got 80 kilonewton, they are to be placed equally from the midspan. If this is your L by 2, and you have to place them equally there, that if this is D by 2 and this is also D by 2, in this way, to get the value of maximum bending moment. This is the criteria here. So you got the D minimum 0.4375. Let's have that. Let's say that our beam is this, and this is midspan 9 meter. This is 9 meter. Now the thing is that we got that critical load of 80 kilonewton. Let's say, and the resultant is on the right of that, is on the left side of that 80 kilonewton. That means resultant is on this side and load is on this side. That means load should be placed here. 80 kilonewton has to be placed here, and resultant is there, and that means 60 is somewhere here, and after that we say 80 is somewhere here, and from this side we say 100 is somewhere here. So we got that concern point of 80 kilonewton. Let's highlight that part. This is our 80 kilonewton, and I would say the critical section for bending moment to be absolute is that section selected is section should be this section, what you call as section is at 80 kilonewton. So this is our critical section. This is our C section. This is our critical section where you can get the absolute bending moment. You won't get maximum bending moment at the midspan. This is not possible for the train of loads. You won't get for this case that at midspan you have maximum that bending moment. The maximum bending moment would be at the 80 kilonewton location, which is at a distance of d by 2 from the midspan, which is at a distance of d by 2 in the right of that midspan. So that our critical section would be. So if I calculate what's the value of A dash for now, what's the value of A dash? That's the A dash is from the support A to the critical section. So A dash is equals to L by 2 plus D by 2. And what is this value now? B dash. So B dash would be equals to L by 2 minus D by 2. So this is your D. This is your D minimum. D minimum. Here we have a resultant of R. Now our section becomes that AB by L, your A dash B dash by L. So finally your bending moment ordinate ILD ordinate at critical location of C would be A dash B dash by L. A dash B dash by L. A dash B dash by L. It's not at the midspan, but it's at some location from the midspan, and the ordinate is YC. Y at critical location C. YC is equals to A dash B dash by L. That is some value of L by 2 was your 9 meter plus D by 2 was your 0.43 some value, 0.4375 divided by 2, 0.4375 meter divided by 2. So you would get a value of that what you have A dash. Similarly, B dash is also 9 minus 0.4375 divided by 2. And this is your AB divided by L. And you can get an ordinate of YC. And ordinate of YC is equals to that equals to 4.4974 meter. 4974 meter. This is our YC. And I had to place the load, critical load at that location now. I had to place the location of that load at this I had to place that critical load 80 kilonewton. 80 kilonewton at this location to get the maximum bending moment, absolute maximum bending moment. This is our 80 kilonewton. And after that, I can place other loads accordingly in a suitable way. That this is your 100 at after distance of 3 meter. This was 3 meter. So this is your one more ordinate. And we have one more load from this side, 60. And one more load of 80. And I had to get those ordinates. And you can calculate those ordinates. This was the length of L by 2 plus D by 2. That is equals to 9.2188. 9.2188. And this length is 2 meter. This is also 2 meter. So this value, this length is equals to, and I can get the ordinates. I would say this ordinate is 9.2188 minus 4. That is 5.2188 divided by 9.2188 into YC. Similarly, this one is 7.2188 divided by 9.2188 into YC. And from this side, I would say this is 3 meter length, and the B bar was equals to, B dash was equals to 8.7813, and this ordinate would be equals to 5.7813 divided by 8.7813 into YC. So you can get the ordinates. So I would say your bending moment maximum, absolute bending moment would be equals to 80 into your value of, let's keep the YC outside, 80 into 5.2188 divided by 9.2188 plus 7.2188 divided by 9.2188 into 60 kilonewton plus then 80 into 1 plus 100 into 5.7813 divided by 8.7813 into YC. Then accordingly you can get absolute bending moment equals to 1070.77 kilonewton meter. So the thing is that in order to get the absolute bending moment for this loading, that you have train of loads. For the train of loads, what is the procedure you have? You calculate that resultant from either of the side. Let's say the centroid is somewhere here. Now out of these two loads, let's say this is P3 and P2, you check which one is your D minimum. You check which one is your D minimum, and you also check that which one is that P maximum, which one is your maximum load. That maximum load, heavier load, we have to keep at that critical section. I would say this should be the critical section. If this is your D minimum, and critical load is B2, I would say at this location, I have to ensure that this length is equals to A dash in a way such that I would say your resultant and P2 they are equally spaced from the midspan. If this was L by 2, and this should be some value of D by 2 also. So finally your section A dash equals to L by 2 plus D by 2. Let's take one more problem. Let's take one more problem. That let's take one more problem. It's saying that you have a point, you have the train of loads. One is your 20, 60, 80, 40. You have this train of loads. And they are moving in the left to right direction. So they have the spacing that 3 meter, 2 meter, 2 meter. 3 meter, 2 meter. Is it the same problem? No, it's not the same. So we had four loads, 40 kilonewton, 80 kilonewton, 60 kilonewton, and 20 kilonewton. Spacing is that 3 meter, 2 meter, 2 meter. They are moving in the left to right direction. Now we need to get absolute shear force and maximum, we can say absolute bending moment at any section, anywhere in the section. So if I say what is the beam looks like, what is the length of the beam, I would say that is 16 meter beam. Now to calculate that absolute positive shear force, that means you have this diagram of absolute positive shear force, positive 1, and you apply the loads at those coordinates. Let's say that you apply 20, 60, 80, 1 and 40, 20, 60, 80, 40 in this way, that this is your 20, 60, 80 and 40, and you get the ordinates also. I would say what is the theta value you can have? What is the theta value here? I would say the theta value is 1 by 16, and the length is between those center to center between the loads is 3 meter, 2 meter, 2 meter, and you can get the ordinates. This one would be equals to 13 by 16. This one would be equals to 11 by 16. This is 9 by 16. 9 by 16. So then I would say V positive would be equals to 20 into 1 plus 60 into 13 by 6 plus 80 into 11 by 16 plus 40 into 9 by 16. So you would get a V positive of 146.25 kilonewton. Now we can do one more iteration. Let's keep it as V1. We can do one more iteration because that smaller load 20 kilonewton is on the peak coordinate. If we keep 60 on that peak coordinate, we can see what is the difference we can have. So same diagram, we have 1 by 16 slope. I'm saying 20 kilonewton is outside the beam. 20 kilonewton is outside the beam. I'm placing 60 kilonewton here. I'm placing 80 here and 40 here. That means this part is 2 meter. This is also 2 meter. Then I can say, what is the slope here? What is the ordinate here? This is plus 1. What is this value? I would say this is 14 by 16. This is 12 by 16. I would say V2 positive absolute would be equals to 60 into 1 plus 80 into 14 by 6, 14 by 16 plus 40 into 12 by 16. And you would get a value of V2 positive equals to, that's greater than with respect to the V1 absolute. So I would say 160 kilonewton. So based on these two values, I would say your V absolute would be equals to 160 kilonewton. Now the thing is that this was with respect to positive. Now we had to see with respect to negative also, that negative shear force. If there was negative shear force, and we had to check that also. Let's go for that. I would say, what is the negative shear force diagram looks like? I would say this is your negative shear force diagram, and you can place the loads. Let's say this is your 40, this is 80, this is 60, this is 20, 3 meter, 2 meter, 2 meter. Theta, what is the theta value? 1 by 16. 1 by 16. And ordinates would be here. This is -1. This is one more ordinate, and we can get those ordinates also. Let's go for the ordinates. I would say the ordinate values would be equals to, this one would be 14 by 16. This one is 12 by 16. This is 12 minus 3. That is 9 by 16. ordinate, then I can say what is the total V negative. We can have V negative 1, that is 40 plus 80 into 14 by 16. Then we have plus 60 into 12 by 16 plus 20 into 9 by 16. So we can have V1 equals to 166.25. 166.24. So I can write a negative here, kilonewton. So if I compare that value with respect to this positive one, so I would say V negative is more. V negative absolute would be more. V absolute negative is more with respect to V positive absolute. So finally, I would say, what is the absolute value we can have? Final absolute value. So V absolute would be equals to, I would take that as 166.25 kilonewton. This is because of the reason that your smaller load of 20 kilonewton, it's having a smaller ordinate, but the bigger loads, they are having a bigger ordinate. That's why in this case of negative, you got a V absolute negative as maximum. You can do one more trial. You can take one more trial that if I place not 40 kilonewton here, if I place 80 kilonewton on this point, if I place 80 kilonewton here and 40 kilonewton outside the frame, outside the structure, there we have 60 and 20, and you would get that V equals to minus 146.25. But I would say you take that absolute value as 166.25 kilonewton. Now for the moment, let's go for the moment now. Let's go for the moment. Let's go for the moment now. Let's go for the moment. Absolute value of moment. Let's go for the absolute value of moment. Let's go for the absolute value of moment. I would take that as, so if I calculate centroid from this side, centroid of those loads, CG of the loads, first step is that for the absolute bending moment anywhere in the section, for the first point is that you calculate the x bar, and that is equals to 40 into 0 plus 80 into 2 plus 60 into 4 plus 20 into 7 divided by total number of loads, sum of all those loads, 80 plus 140. So you got that 2.7. That means from this point to this point we have some 2.7. Here we have some centroid of R. That CG of loads at R. So if the x bar was equals to 2.7, that means your part of this one would be 0.7. That's also D minimum based on these two values. This one is 1.3. So and the load is also lesser. So I would select this load now. Let's say that if this was length of 8 meter and this was 8 meter length, I had to ensure that the resultant and the concerned load of 80 kilonewton, they should be equally spaced from the midspan. If let's say there was some resultant here and the 80 kilonewton was here, I would say this part and this part, they are both equals to D by 2, D minimum by 2. So I would write them these values as, this is your D minimum by 2 and this is also D minimum by 2. That's some value of 0.7. 0.7 by 2, that's 0.35 from this side, 0.35 meters from this side. Now the thing is that what should be the critical section now? I would say the critical section should be such that at that location the critical load should be placed there. Now I would say, what is the critical load? What is the location of that critical load? That is what you can call as A dash from the support A. So I would say your critical load is acting at this point, that is at 0.35 meter from the in the right side of that center of the beam. So that's your critical load of 80 kilonewton, and the other loads can be placed in that same fashion. We can have, I would say 80 kilonewton is acting here, 40 kilonewton would be somewhere here, and 60 would be somewhere here, 20 would be somewhere here. Then finally I would say, what is the critical section? That C, that means this C is your critical section, and what is the value of A dash? That is equals to 8 plus C, that D by 2. That means 8 plus 0.7 by 2, that's 8.35. And what's the value of B dash? I would say B dash would be equals to 8 minus 0.35, that is 7.65. So I got the value of ordinates of that critical section C. I would say you have some section C. Here the ordinates are in this fashion, that AB by L. AB by L, that value of YC would be equals to AB by L. Then I have the ordinate value YC equals to YC equals to 3.9923 meter. I would say this length is 8.3 meter and this one is 7.65. So the absolute location for the location for absolute bending moment anywhere in the beam would be at when this from the support A, you go from support A to a distance of L by 2 plus D by 2. Then you have to place at that location that maximum critical load. So when I place that critical load, then after that I have to ensure that all other loads are placed accordingly. So I would say there is some 40 kilonewton acting here, and after that from this side we have some 60 kilonewton acting, and we have some 20 kilonewton also acting from this side. And we also know that the distance between those loads, this one was your 2 meter, this one 2 meter, and this one's 3 meter. And I can now calculate those ordinates. Can you tell me what is the ordinate here? I would say we have some value of YC at the critical section C, and I would say here the ordinate would be equals to 5.65 divided by 7.65 into YC, and from this side we have the length of 8.35. So I would say this ordinate would be equals to 6.35 divided by 8.35 of YC, and similarly this one 6.35 minus 3, that is 3.35 YC divided by 8.35. So if I have these ordinates and you multiply with the load, and I can get the maximum absolute bending moment in the beam. So that would be equals to 20 times, let's say the YC is outside. I would write 20 into 3.35 by 8.35 plus 60 into 6.35 by 8.35 plus 80 into 1 plus what we have that one more load of 40 kilonewton into ordinate of 5.65 divided by 7.65 times YC. So we can have that M absolute equals to 651.524 kilonewton meter. So what is the conclusion that we can have for the absolute bending moment for the beam when there are train of loads, wheel loads? So we say first step is that get the centroid of those loads. Get the centroid of those loads x bar, and it might be between two loads. Then out of those two loads, you need to find which one is heavier load. You need to get which one is heavier load. Then we have to say this load P2, this is P heavier, and I would say your resultant are P heavier and resultant are they should be equally spaced from the midspan. That such that if the distance was between them d minimum, that means distance from the center is d by 2, and this one is also d by 2, and accordingly our section becomes critical at the location of P2 at this heavier load. Then accordingly I would say this is your value of A dash and this value is B dash, and I have the ordinates of A dash B dash by L, and accordingly I can adjust other loads in order to get the absolute bending moment in the beam. So in these problems we solved that our centroid was on the left side of that critical load. Now the next problem is that where your centroid of the load is on the right side of the load, right side of that critical load. Let's go for that. case. Let's go for that case. So this is the problem that we have train of 5 wheel loads. So we have 5 wheel loads. 5 wheel loads we have. One is your 80, 80, 200, 180, 120 kilonewton. So they are acting in this way. And the spacing, we say, spacing is that this is 2 meter, this is 2 meter, this is 3 meter, 2, 3, 2, 3. 2 meter, 3 meter, 2 meter, 3 meter. They are moving in left to right direction. And we have beam of what you have. We have the beam of 24 meter. We have the beam of 24 meter. Beam is equals to 24 meter. And we need to get what is the maximum positive, maximum negative shear forces at center of the that's at center of the beam. That means at your section becomes x equals to 12 meter. At x equals to 12 meter. So, and we had to also get the absolute bending moment anywhere. Second part of the problem is that you go for the absolute bending moment anywhere in the beam. So we have two cases of this problem. First one is that you calculate the positive, negative values of those shear at the midspan. So let's go for the beam of 24 meter. Beam of 24 meter at the midspan. If you have the section at the midspan, that means your ILD for the shear force would be in this fashion. So this one was your 12 by 24, that's 0.5, and this one is also 12 by 24, that's 0.5. Now for the positive side, let's go for the negative side first. I have this negative side. Let's make the straight line. I have this negative diagram, negative shear force diagram, not diagram, shear force. This is the ILD, negative part of the ILD for your shear force at section C midspan. So let's go for that. Let's keep the loads in this way. Let's have those loads in here. Let's keep those loads here. Let's say these are our loads. Let's say these are our loads. We have these loads. So we have these loads. I would say this is 2, 3, 2, 3. And these loads I can place because they are moving in the left to right direction. So I have to place them suitably. So they are moving in the left to the right direction. So if I place them in this way, if this was your 2 meter, this was 3 meter, this was 2 meter, this was 3 meter. Yeah. Let's have those ordinates. What is the theta we can have here? That's 1 by total length of 24. I would say this is ordinate of 0.5. What should be this ordinate? What is this ordinate? What is this ordinate? I would say this ordinate would be equals to this ordinate is 0.5. This one would be we can write what is the total length we can have. This total length is equals to 12. Length of this part is equals to 12. L equals to 12 for this part. So I would say this value, this is also equals to 12 by 24, and this value would be equals to 9 by 24, and this value would be equals to 7 by 24, and this value would be equals to 7 minus 3, 4 by 24, and this value would be equals to 4 minus 2, that's 2 by 24. So we have these ordinates. 2 by 24, 4 by 24, 7 by 24, 9 by 24. Okay, and we can write V negative at section C, that's at center. We can write that is equals to 120 into 0.5 plus what we have 180 plus 180 into 9 by 24 plus one more thing is 200 into 7 by 24 plus we have one more, that is 80 into 4 by 24 plus you have 80 into 2 by 24. You got these and you can add them, and that is overall negative value of minus times, I would say that is 205.833 kilonewton. So this is your negative value of that. Then one more thing is that if you try iterations, there is not that much possibility of that, because this is 120, this is also 180, so there's not a significant difference, and there I would say your value would not differ so much. So you can keep this value as V negative maximum at the center. And if you want to calculate V negative, V positive at the center, let's go for that now. Let's go for that. Let's take these loadings together. Let's copy that. Let's move that. let's move these loadings we already have. So let's place them in this way. So the line was in this fashion. I would take that part. So if the loadings is such that they are moving in this fashion, so 80 kilonewton has to be applied at this peak, at this peak ordinate. So now the case arises that if this was a length of 12 meter, this is length of 12 meter, and theta here is 1 by 24. This is ordinate of 0.5, that's 12 by 24. And I have to adjust to these. I have to compress it a little bit. Yeah. So I would say, what is the ordinate here? 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 I would say the length is 2 meter, 3 meter, 2 meter, 3 meter. So ordinate here would be 12 minus 2. That's 10 by 24. Let's make it a different color. 10 by 24. This one is 7 by 24. This one is 5 by 24. This one is 5 minus 3. That's 2 by 24. We have these ordinates. And we can directly now calculate that what's the V value we can have. I would say V, let's calculate it as V1 positive, because there are these loads 80 kilonewton, they are smaller as compared to 200 180. So then we can do one more iteration for this one. So if I write V1 positive, so I would write 80 into 0.5 plus 80 into 10 by 24 plus one more thing is that 200 into 7 by 24 plus 180 into 5 by 24 plus 180 to 2 by 24, and that value is equals to 179. Yeah, that value is equals to 179.167 kilonewton. Now second case we can try second case, that if the loading is adjusted now, if I'm going to adjust to the loadings. So let's adjust the loadings in this way. Let's say that one of the 80 kilonewton is outside the frame, outside the positive diagram. Then I have to subtract its effect also, because we are talking about positive negative. So its effect would be there. I have to calculate that ordinate also. Because of this part only, it would have been contributed more, but because this 80, we had to subtract this effect also. So we had to check that effect also. So I would say this ordinate would be, this was your 2 meter, and total length was 12. So this one would be your 10 by 24 ordinate of 10 by 24. And if I write that values of, if I write now the ordinates might differ. Now. Ordinates might get changed. I would say if the diagram is in this fashion, let's say positive diagram is in this fashion. So I would say total length was 12. So this would be your 9 by 12, 9 by 24. I can say ordinate of 9 by 24. This ordinate is what we have. This ordinate would be equals to 9 minus 2, 7 by 24. This ordinate is 4 by 24. 4 by 24. Let's go now for the V. What we have? V. Yeah. So V positive 2. So we can write that also. Let's go for that calculations. I would say that we can keep the 24 outside, that we have kept it as a common for each of the terms. So I would say your 80 kilonewton negative into ordinate of 10 plus, then after that all positive values. After that we have all positive values. We have that all positive values of 80 into 12 by 24 plus 200 into 9 plus 180 into 7 plus 120 into 4. So we have these values, and we can get the value of V2 positive. So that is equals to 154.167. That is lesser than the initial value. So I would say your V positive absolute would be V positive maximum at the midspan is equals to 179.167, and V negative maximum at the midspan equals to 205.83 kilonewton. So let's go for the what we have. We have that maximum absolute bending moment. So we had these loadings of 120, 180, 120. Then one was, let's make it in a clean way. I would say you had these loadings One was a loading of 120. After that we had 180. Then after that we had 200. After that we had 80, and after that we had 80. 2 meter, 3 meter, 2 meter, 3 meter. If I want to calculate the centroid, let's go from this side. I would say, what is the CG of the loads? I need that absolute bending moment anywhere in the beam. Anywhere in the beam. So I would say, what is the centroid from the right side? I would say that equals to 120 into 0 plus 180 into 3 plus 200 into 5 plus 80 into 3 3 are 6 plus 3 3 plus 3 plus 2, that's 8 plus 80 into 10 divided by total number of loads, summation of all those loads, and you would get a value of centroid equals to the value of centroid equals to 4.5152 4.5152 meter. So let's have that. I would say this is your 3 meter, and total is 5 meter up to this point. That means 4 is somewhere here, and 4.51 is somewhere here. So this is our resultant of the loads. Resultant of the loads is somewhere here. So resultant of the load is somewhere here. Now if you want to say what is the value of D minimum, so I would say that D minimum would be corresponding to the bigger load also, and we also see that D minimum is out of these two loads. Critical is 200, and D minimum is also from this side. So D minimum is equals to, we have that 0.4513. We have that 4.4, total length of that centroid was 4.5152 4.5152 meter, and total length up to the point 200 kilonewton was 5 meter. This length was 5 meter, and this part is only that x bar. So your D minimum is equals to difference of the two. So 5 minus this much. So this is your D minimum, and that value is equals to 0.4848 meter. So this is our D minimum. Now we have to place that. Now for the maximum absolute bending moment in the beam, let's say this is our beam, and the length of beam was how much? How much was the length of beam? Do you know how much was the length of beam? 24 meter. We say for the bending moment to be maximum under any point load, the resultant of the loads and the point load, constant point load, they should be equally spaced from the midspan. Let's say the midspan is here. I would say this is 12 meter, and this is 12 meter. This is the midspan. Now we see that where is the centroid? On what side of the section we have centroid? I would say, if you compare that, this is our critical load 200, and centroid is in the right side. That means centroid is from this side. So I have to keep in this fashion. These two I have to keep in this fashion on the beam itself. So 200 is on the left side, and R is on the right side. It is the inverse of what was in the previous problems we had. R was coming out to be in the left side, and critical load of P2 or any heavier load was coming on the right side. So let's have this case now. 200 is on this side, left side, and R is on this side. So I have to keep them equally spaced from the midspan. So this is our resultant, and we have some load of critical load of 200. So that means our section, that A dash B dash becomes, your A dash becomes L by 2 minus, as you can see that this is some D by 2. Total was L by 2, and you have to subtract to get the critical location. L by 2 minus D by 2, and B dash would be equals to L by 2 plus D by 2. This is the reverse of the previous problems we had. Here we have A dash lesser than B dash. So your critical section is that under the heavier load. This is our critical section C. So under this section we can get the ILD for that beam. So this is our critical section. On this section we have to keep that critical load of 200 kilonewton. This is our 200, and accordingly we have other loads also. We have other loads of that we have 200 from this side, 180, 120, 180, 120, 180, and 120. From this side we have two loads of 80. 80. Yeah, this is 2 meter, 3 meter. This is 2 meter, this is 3 meter. And I can get the ordinates now. I would say, what is this value of A dash? This value of A dash is equals to 12 minus D dash, D by 2. That's 12 minus 0.4848 by 2. And you can have that value also. That's 11.7576. And similarly, B dash is equals to out of that 24 minus A dash, 11.7576. So this is 11.7576 meter. Accordingly, we have B dash equals to 24 minus 11.7576. Then I can say what are these values of ordinate? What are these ordinates we have? We have YC. Let's say this is YC. YC is equals to A dash B dash by L, and that we have already. We can solve that. 11.7576 into one more ordinate of 12. Is it 12.2424? 12.2424. I think B dash is equals to 12.2424. 12.2424. If you have this value, it is 11.2424 divided by 24, and you have a YC value of, we have solved that, YC 5.99 meter. YC equals to 5.99 meter. So I would say, what are these ordinates? Let's go for those ordinates. This ordinate would be equals to 12 minus 2, that is 10.2424 divided by 12.2424 YC, and this is 10 minus 2, that is 7.2424 divided by 12.2424 YC. And what is this ordinate from the side? I would say this is YC for the length of 11.7576. 11 minus 3, that's 8. So I would write 8.7576 by 11.7576 into YC. And this ordinate you have 8 minus 2, that is 6.7576 divided by 11.7576 YC. So we have these ordinates. You multiply those loads with the ordinates, and you can get the V absolute, that M absolute anywhere in the beam. M absolute, that is equals to 80 into 6.7576 divided by 11.7576, and you keep the YC outside, and plus one more load of 80 into 8.7576 divided by 11.7576 plus 200 into 1 plus from the other side we have 180 into 10.2424 divided by 12.2424 plus 120 into 7.2424 divided by 12.2424, and entire multiply with YC. So you have that absolute bending moment value of 3157.64 kilonewton meter. So thank you for watching our series of influence line diagrams. I hope you got the entire things what's happening with those influence lines. Thank you for watching our series. All the best. All the best. Thank you. Thank you. Thank you.